Okay, so yeah, this is my first time live streaming. If anything doesn't work, if you can't hear anything, if you can't see anything, just let me know, and I'll do my best to try and correct that as quick as possible. So today's topic is on traffic flow theory. We're going to just jump right in. We're going to talk about a few of the major things that are most important in traffic flow theory. So we're going to talk a bit about flow density relationships. So how does the flow rate on a road vary with the density of total numbers of vehicles per kilometer? And we'll see there's some interesting relationships, some of which are reasonably intuitive, but there's some nice ways of thinking about traffic flow that come out of that. We'll look a bit at the some of the fundamental diagrams of traffic flow. So just seeing how we can think about distance and space and time relationships for vehicles moving along a stream. We'll talk about the concept of lane metering. So you might have seen this on highways in Melbourne, possibly in other places in the world as well. I mentioned in previous lectures that Australia and Victoria in particular has the longest continuous sections of metered managed motorways. So that's where only a certain number of cars are led into a traffic stream in a given period of time, and it really helps to maximize the efficiency of that traffic stream. We'll talk a bit about traffic modeling as well. So there are a few manual modeling methods that we will discuss very briefly, but for the most part we're going to talk about some of the broader scale software packages and systems that are used for modeling software or modeling traffic. And we'll also talk about measurements of capacity, so how many vehicles can fit on a given road. It's reasonably static per lane, but lane width does have something to do with it, as does speed limit. And we'll talk about level of service, and that's basically how happy people are, a scale of A, B, C, D, E, F, from A being the best performance of a road and really happy drivers, down to people that are stuck bumper to bumper and they're really quite upset. As I said, jump out in the chat, type anything if you've got any questions. Hayden, is there anything you'd like to add there? Nope. All right, we'll press on. There's a few references to different parts of Ostroad's guides and some other traffic engineering manuals. It's not necessary for you to jump into those. I'll make specific references to other appropriate parts of Ostroad's guides and other VicRoads guides as we go along. Okay, so one of the first things that I want to talk about is the concept of flow. So what do we mean by flow or traffic volume? This is also put up here. So typically what we're talking about in terms of traffic flow is a volume of vehicles per hour. We can be talking about vehicles per day, as in the case of AADT, annual average daily traffic. But flow rates, when we're talking about the function of an intersection or the function of a highway, and when we're worried about flow breakdown and that sort of thing, it makes most sense to measure in vehicles per hour. So if we want to find the value of flow, as Q being our symbol for traffic flow, we take the number of vehicles divided by the time in hours, multiplied by 3600. So, number of vehicles passing a road point in a certain number of seconds. So it may be you've got 0.1 vehicles passing because it's one vehicle every 10 seconds. Then you've got a rate of something more like 360 vehicles per hour. But in general, as long as you have if you have all of your units, you're putting all of the units, however you're measuring traffic, maybe you're measuring in 15-minute blocks, so you might have 500 vehicles per 15 minutes. If you multiply out by the number of 15-minute blocks in an hour, you'll come to a vehicles per hour relationship. Please let me know if any part of that is at all confusing, and I'll jump back to it. Another key topic, or another key concept in traffic flow is density. So this is the number of vehicles traveling over a unit length of highway in an instant of time. So we usually measure this in a 1 kilometer length. So if we were to say that we have a certain number of vehicles per kilometer that we can fit on a road, that gives us our measurement of density. Now, as you might imagine, the lower the density, the more comfortable you are as a driver, the more space you have to move around. And as that density increases, there is a certain theoretical maximum density when cars are literally bumper to bumper, that that is the highest theoretical density we could fit. And in practice, the true density is significantly lower than that because we need to have a certain amount of space between each vehicle's start and end bumper. And we also will note that that amount of space that we want to see between vehicles, it changes with speed limit. And that's partly why when the density becomes very high, the speed limit, or not even the speed limit, but the speed of vehicles in the stream has to come down. So we're talking about those really traffic jam type scenarios, that that bumper to bumper arrangement. And speed, well, this is the same concept that you've seen in every other location. It's just distance over time. Specifically in traffic flow, it's distance traveled by a vehicle during a unit of time. So we can look at this a few different ways depending on what we want to find out. Speed is quite often measured in terms of the speed of a particular vehicle or the average speed of vehicles passing a point, but we might also say things about speed when we are interested in particular safety outcomes. We might not want to know what the average speed is, we might want to know what the 85th percentile speed is. So in other words, what is the speed limit which is not exceeded by 85% of vehicles? So 15% of vehicles are going faster than the average. What is that key point? And then we can make some sort of design outcomes by looking at that higher level of speed. So to sort of elaborate on a little bit further, if you have an 80 kilometer an hour speed limit, possibly the average speed is 80 kilometers an hour, but the 85th percentile speed might be 85 if you've got reasonably good compliance. In other words, reasonably good people are obeying the speed limit reasonably well. If you had an 85th percentile speed of 90 or 95, that would tell you that, yeah, most people are doing the speed limit, but a lot of people are speeding by a wide margin. And that can tell you things about the sort of roadside environment. People might see an 80 kilometer an hour speed limit, but they also see a very wide stretch of road with a very straight, good viewports, no intersections, and they think this doesn't feel like an 80 kilometer an hour speed limit. So the road environment and the speed limit need to match, otherwise the speed of vehicles won't really match the speed limit as well. Hayden, is there anything you'd like to add on to that one? Can't hear anything coming through, Hayden. Have you got a physical mute?
Is that better?
That's better, yes. Yep.
Okay, sorry about that. Yeah, as you've seen, I think RRV last year or the year before copped a bit of flack from dropping the speed limit of roads from 100 to 80, and that's the reason why is the infrastructure of the road is a lot can handle a lot speeds a lot faster than 80. So as you see that, especially around here, around Melbourne North, from Melbourne North to Dumbalk, they dropped the speed to 80 kilometres per hour. When it used to be 100, people have travelled that road at 100, and even when you know that it's 80, it's very hard to stick to the 80 speed limit because the road feels like you should be travelling faster.
Yeah, absolutely. That causes a great deal of grief. There's a lot of roads in the States. I'm not familiar with the particular ones that you just mentioned then, Hayden, but I know there's a lot of roads where the average speed of drivers is about 80, despite being signed at 100, and a lot of those roads are being flagged for potential speed reductions to 80. But then you do get 20-30% of drivers who get very upset with that because, exactly as you say, the speed limit does not feel like it matches the road. When one of the biggest dangers and what's trying to be corrected there is that differential speed between some people traveling at 80 and some people traveling at 100. Can I just get confirmation in the chat that everyone can hear myself and hear Hayden okay? So I've just got silence because I don't know how long the delay is. There we go, can hear. Yeah, loud and clear. All right. So I think the delay is a bit larger than initially I was. Yeah, okay. All right. So thank you, everyone. Thank you. Yeah, so the delay looks like it might be 20 odd seconds. So what I'm going to do is I'm going to ask a question. and then I'm going to press on. But please feel free to write a response, and I'll keep an eye on the chat, and then I'll just go back in the slide if anyone has a question. So thank you very much for that. Okay, another point to note is time headway. So this is the difference between the front of a vehicle, or the time that a front of a vehicle arrives at a point, and the time that the front of the next vehicle arrives. This is a similar concept, time headway and space headway. These are similar concepts to describing wave functions. So if you remember in the discussion of waves, we have a sort of a crest and a crest, and the distance between the crest and the crest, we can define that as a wavelength. Similarly, if we have a car, and I'm going to do a really bad drawing of this, a car and another car, we can sort of define a kind of a wavelength as being between the same point on two consecutive cars. So this is a sort of the same concept. If you've seen that before in wave theory, it's the same kind of thing we're talking about here. So we've got time headway, so we can measure that as a sort of time distance between vehicles, or space headway, which is more of a wavelength type of function. So we can start to define a few relationships. I'm not going to go too heavy into the math on this sort of thing. I don't want to go make it too complicated, but some simple relationships that we can infer quite easily. If flow is number of vehicles per unit time, and time headway is time divided by number of vehicles, we can say that flow is 1 over time headway. So if we can see it's 3 seconds between vehicles, then we know we must have 1,200 vehicles an hour, if you do the math on that. We've got another relationship that we can see. So density is number of vehicles divided by distance. Space headway is distance divided by number of vehicles. So again, we have this reciprocal relationship. Density is 1 on space headway. Now we can start to do some other things with this. So if we know that the space headway is the speed, this is in meters per second, multiplied by the time headway in simply seconds, or just some unit of time and some unit of distance by time, the product of this has to be a unit of distance. So that's where we get the space headway. And we can also say that flow, so this is vehicles per hour, must be equal to our density as vehicles multiplied by our distance per unit time. So we'll be able to work out what our vehicles per kilometer multiplied by kilometers per hour, we'll be able to get back to vehicles per hour. And that's just looking at the units. If you were to sort of expand the units on each of these, flow has units of vehicles per, and sorry for my terrible handwriting, I'm just using a mouse to try and draw this. So we've got vehicles per hour here, we've got vehicles per kilometer here, and we have kilometers per hour. So kilometers cancel when we multiply these together. Vehicles per hour is vehicles per hour. So we can also see that the speed must be the flow rate times the distance headway between vehicles as well. Let me know if there are any questions, but I'll press on. So we have a few different kinds of traffic flow that we can talk about. These are a few key terms. If you check your key lecture questions, you can see that question 2 is on. Oh no, it's not question 2. Sorry. Question 4 is on this slide, and the previous 3 questions were on the slides that we just covered. So interrupted flow, as the name might suggest, this is flow where there's some kind of stop-start relationship. So we have traffic signs, traffic signals, we have crossing roads which are not separated in time, not separated in space, so a typical cross intersection like this. If we've got vehicles that want to travel this way and vehicles that want to travel this way, we need some way to separate them in time. So we might use some give way marking here. And the flow here would be interrupted. So this one is interrupted. Uninterrupted flow, this is where vehicles are not required to stop for any reason. So this would be on a freeway. And that's sort of how we define a freeway. That keyword free in the start is basically saying that there's nothing that gets in the way to stop you. Freeways are continuous sections of uninterrupted road. There's no traffic signals or give way signs. If we have to introduce a traffic signal, say to improve the safety of an intersection, if we've got to introduce a traffic signals on a freeway, we have to downgrade the definition of that freeway to a highway. So the Western Highway travels beyond Ballarat, and it's interrupted in some places. If you go through Beaufort, there's a set of traffic signals that you come across on the Western Highway. But if you take the Western Freeway from Ballarat to Melbourne, there's nothing that stops you. You get slowed in some places from 110 to 90 or 110 to 80. But in general, that's an uninterrupted flow freeway condition. We can, for an uninterrupted flow where we've got no sort of external crossing points or nothing else that troubles us, we can give ourselves a few simple cases to talk about. We've got a flow rate, which is a constant density, flow rate at a constant headway, so constant spacing between vehicles, and flow rate at constant speed. We'll talk a bit more about these shortly. Hayden, is there anything you want to add or talk about further there?
Not at the moment, no.
Yep.
You're covering it good.
Great, we'll press on. So flow at constant density, this occurs when we have all vehicles traveling with the same space headway, and all vehicles are at the same speed as well. So we've basically got the same distance between each vehicle. The density is not changing from moment to moment. This is not realistic in terms of how we typically see vehicles moving on the road, but it is ideal if we could get vehicles to travel at constant density, as we'll see in a video that's coming up shortly. We would have fewer issues with congestion and fewer issues with sort of bottlenecks that start on the road and slow traffic for long periods of time. A lot of these are really talking about a similar sort of thing. If we've got constant density or constant time headway, then this is really the same concept. We've got the same amount, presuming the speed is the same, we have the same amount of distance between vehicles as well, and therefore the same density. If we have flow at constant speed, then we must have all vehicles uniformly moving. Perhaps there are pockets of vehicles that are 1, 2, 3, 4, 5 vehicles in quick succession, and then a gap, and then 7, 8, 9, 10 vehicles, that they can all be traveling at constant speed, but not necessarily at constant time headway or constant density. So, as we discussed briefly before, there is a connection between traffic density and vehicle velocity. If we have more vehicles on a road, they will tend to be slower. They have a slower velocity. And this is, as we'll see some curves coming up shortly, some graphs coming up shortly, there's a sort of an ideal point. We can, if we want to increase flow rate, we can increase density up into a critical tipping point, and then beyond that tipping point, we start to really drastically slow velocity and therefore slow flow rate. So in terms of preventing congestion and keeping traffic flow stable, we want to make sure that the number of vehicles that enter a control zone, so this is a traffic stream that we're trying to control, we want to make sure that the number of vehicles entering is smaller than or equal to the number of vehicles leaving the zone in the same time. So here we've got sort of a bit of a diagram of a lane metering arrangement. We are controlling the number of vehicles that are coming in, so all of these red vehicles are stopped. The green vehicles are being incrementally released so that they don't oversaturate the capacity of the major highway in here. Now we have also, as I sort of mentioned before, a critical density and a critical velocity that we can sort of, it's a little bit like the critical and supercritical flow relationships, talking about hydrodynamics. If we're talking about fluid theory and the change between laminar and turbulent flow. If you recall your study of fluid mechanics, you'll recall that as we increase velocity, as we increase the amount of momentum or energy, that inertial forces that are present in water, we can go from a laminar flow, which is stable and which is predictable. We can perform mathematical calculations on this stable flow, and they come out to be very true. But if we're in a certain range, the flow can flick between this sort of stable and this unstable, so this laminar and this turbulent flow. And the same thing is very much true with traffic flow as well. We can have a range of critical densities. As we're approaching a critical density, we could see sort of pockets of people having to brake and accelerate, but the flow is generally traveling pretty well. At a certain point, if we tip that little bit too much further, there'll be a complete flow breakdown. People will have to brake very hard in succession to avoid collisions, and that will form a long-lasting slow traffic condition. Hayden, is there anything you'd like to add there?
No, all good.
Very good. So, if one of the vehicles brakes in an unstable flow regime, the flow will collapse. Think about you're traveling with, maybe the density's gotten to the point you'd like to have 2 seconds or 3 seconds between you and the vehicle in front of you. That's ideal. And you're all traveling at about 100 kilometers an hour, 2 or 3 seconds gap. Yeah, that's reasonably good. You're happy with that. But you're getting closer to Melbourne, and you're getting closer and closer to peak time, and so the density of the vehicles is increasing. More vehicles are merging, and so you slow down a bit to let one in front. That brings you closer to the vehicle behind. The vehicle in front also merges in closer to you. So now you've only got 2 seconds, or maybe you get down to 1 second between you and the vehicle in front and the vehicle behind. So you slow to about 80. That feels a bit better. You're still traveling at about 80 k's an hour. You've got about 1 second between you and vehicle in front. But when everyone is doing that, and all of a sudden someone has to brake because, I don't know, they took their eyes off the road for a second to read a text message, or a bird flew in front of them and they broke to avoid hitting the bird, or something like that. The person behind them has to brake harder, the person behind them brakes harder still, and we have a collapse in the flow regime. So we have this red light condition where you're staring at tail lights for potentially a long period of time. So this gives us one example of, or one diagram that shows us how speed and flow are related. And you can see here by the way that we have sort of two y-axis positions for any x-axis position as we're looking along here. This is not a true function. We can't sort of plug in a flow rate and get a speed. There are multiple potential speeds and flow rates that are present. But our sort of ideal position is some balance in between. If we continually increase flow and increase flow, we need to pick up speed in order to do so. Or it's sort of more like looking at it this way. If we start with a high speed limit, we can increase our flow by decreasing our speed. But then at a certain point, if we try to push this too far, our speed will tend to go back the other way. So there are quite a few diagrams we'll look at that help to explain or give you some ways of thinking about how vehicles can be thought of to flow and how their flow can break down. And this is one of them. If it doesn't make too much sense right now, don't worry too much about that, because we'll see a few more in some moments that will hopefully be a bit clearer. Once again, Hayden, do you want to add anything there?
No.
Yep.
No.
Great. And students, let me know if you have any questions. We're happy to answer anything in the chat or in Discord or anything like that. I'll just quickly check actually, how many people do we have watching the live stream? 15 people right now, so that's pretty good actually. That's most of the class, I think. Okay, so this fundamental diagram of traffic flow we saw on the last slide, this shows the relationship between, not this one, sorry, on the next slide I think we'll have it, relationship between density in vehicles per kilometer and flow of traffic on a highway. So we can sort of think about some of the logical consequences of being at different points on a relationship between density and flow. If we have a density of 0, then we must also have a flow of 0. We've got no vehicles, so that only makes sense. So we've got a 0, 0 condition. And we can say that as the density increases, the flow must also increase up to a certain point. So when the density reaches the maximum, we refer to this as the jam density because it makes a traffic jam. The flow must also be 0. So at a maximum density, we also have a 0 flow. Vehicles will tend to line up end to end. This is that bumper-to-bumper condition. At 0 speed, you're pretty comfortable being as much as a meter from the vehicle in front of you. But as the speed increases, you must decrease your density because you're not comfortable traveling at 10 kilometers an hour even, unless you've got a car length between you and the car in front. So it follows that as density increases from 0, the flow will also increase from 0 to a maximum. But if we increase the density further, so further continuous increases in density, this will reduce the flow, which looks like this. So we've got flow on the vertical axis, we have density on the horizontal axis. We can start by increasing flow, we increase density. We get to our maximum density, our critical density. And as we increase beyond that, we start to decrease our flow. And in this area, this is sort of, if we're on the left of this dotted green line, we're in our sort of stable laminar flow. And then on the right side, we start to approach that sort of transition range. And then I guess beyond point B, you can sort of think about as being your truly turbulent range, to use the language of fluid theory. If we draw a line from the origin to particular points on the curve, then we can see a slope in here, which shows us the mean speed. So we can sort of measure density is vehicles per kilometer. We've got flow rate in vehicles per hour. If we take a slope of these lines, this gives us a kilometer per hour sort of arrangement. If we look at the tangent from the origin, so tangent from 0, 0, coming straight out here, this curve, this tells us the mean free speed. So this is the speed limit, which is, or not the speed limit, sorry, this is the speed of vehicles when there's nothing in the way. When there's nothing to slow them down, they can basically travel at whatever speed they want, which will tend to change with the speed environment. If you've got as I mentioned before, a narrow road or a road with sharp drop-offs or a curving road, the slope will be lower. But if you've got a clear straight road with safety barriers, wide shoulders, all that sort of thing, then we'll have a nice steep high mean free speed in there. So we've got a couple of questions that we've recently come past on our key questions list. What is meant by the stability of traffic flow? So we've talked a little bit about that. Hopefully you've got some idea on what stability means in traffic flow. And also question 7, describe how traffic flow varies as density gradually increases from 0. What happens if density continues to increase? So that's what we're seeing on this slide here. Okay. So we've got another flow here which looks at the change between space mean speed, so it's the average speed of vehicles along the road, and the flow rate. And again, we can start with a high average speed. As we increase that average speed, as we decrease the average speed, we can fit more vehicles on the road. This is an uncongested area. And then as we continue to, I guess, play with trying to add more vehicles or trying to change the sort of speed relationship, we enter this congested area. So as we've mentioned before, this is kind of why we try to use lane metering. This is why lane metering is effective, because if we just keep trying to let vehicles shove themselves into a particular highway, they end up congesting that highway and the flow actually decreases. So we're able to move fewer vehicles. But if we have electronic variable speed limits so that we can change the speed, lower that in key areas to avoid and break up traffic jams, we can decrease the number of vehicles entering a flow. We can stay in this green section and we can keep moving the most vehicles per unit time. Hayden, is there anything you'd like to add there?
No, that's all good.
Cool.
Yeah.
I might just I'll keep talking, and then if you want to just jump in at any point, just unmute yourself and yeah, say a quick hey, and we'll go from there.
Yep, Will do.
Another relationship between the mean speed and the density shows us that if we have maximum density, we must have no speed. If we've got a zero density, then our space mean speed is quite high. And we've got this sort of negative linear relationship. Again, these are diagrams. I'm not going to ask you to repeat these diagrams from memory. If you can describe something about the relationship between how the speed of vehicles changes with changing density, then I'll be happy with that. So we've got a few different ways that we can model traffic flow, a few different mathematical relationships for traffic flow. So we can either talk about them in a macroscopic approach, which is to say that we have a flow and density which is related to mean speed. So flow relates to density and space mean speed. And this is looking very broadly. Macroscopic means it's sort of a broad overview. So we're not, in this area, we're not taking into account things like the position of intersections. Pardon me. We're not taking into account the need to slow down and give way and that sort of thing. We're just looking at how flow on different networks will change as we try to input more vehicles onto particular areas. In our microscopic approach, this looks more at individual cars. So we look at car, it's also referred to as a car following theory, but this looks at the spaces between and speeds of individual vehicles. Where these two models are used will vary depending upon what you're trying to get out of your analysis. So if we want to model a particular intersection and we want to know what is the capacity of this roundabout or what is the level of service of these traffic signals, we can input all the different demands on vehicles wanting to turn straight, also go straight, turn left, turn right. We can look at all of that and we can figure out how many vehicles are getting through, how does that relate to the demand, and what's the level of service. But if we want to know broad things, like how many vehicles are able to move across Ballarat, or how many vehicles are able to move through the Melbourne CBD, and where are the choke points in the Melbourne CBD, then we would use a macroscopic approach. So we would just sort of look at, again, to use an analogy to fluid mechanics, macroscopic approach is kind of like looking at a whole series of pipes in a water main distribution network. We want to move water around the main network, and the water can take as many different paths as it wants to get to its end goal. Whereas the microscopic approach is looking at an individual T-section bend. We're trying to calculate how much water is going left and right based on the pressure on either end. No, let's talk quickly about shock waves as well. Now, I'm not sure exactly how we're going to do this next bit. Maybe we'll try watching the video together. But I've got a video that explains shock waves really well. But basically what happens in a shock wave is there's some kind of change in the capacity of a highway. Now, this can be triggered by something that's permanent, like a reduction in the number of lanes, or it could be in something that is temporary. So a vehicle swerves or breaks down and closes a lane temporarily. And what we need to do is then think about, okay, how does that sudden change in flow rate affect the vehicles that are also that are further back on that road? Where does the shock wave move? So all the vehicles, let's say all the vehicles are traveling in the north direction. We've got a 4-lane highway. All the vehicles are traveling in the north direction. Suddenly we have a breakdown or a truck rollover or some horrible thing, and we're down to 3 lanes. Now all the vehicles are traveling north, but the shock wave actually moves south. The shock wave will travel backwards in the space relationship. It will increase the density of flow. It will decrease the speed. It will decrease the flow rate as we follow this shock wave back up the traffic flow. And what we see is that we've basically, if we see the volume on the vertical axis of this graph, we see that we've started with some capacity C1, and then after some incident, so like I said, a truck rollover or something, we come to C2, so this lower volume. Now to fit the density, the sort of same vehicles are trying to use this space, but now we have a lower capacity. We've got a lower space mean speed, so that axis here will need to change. We will also see that there is a sort of a speed rate. So on this this graph between volume and density, the linear relationships, the lines that we've drawn here on these angles, these are velocities. So the slope of this velocity from this point here at the flow rate 1 and capacity 1 coming down to flow rate 2, capacity 2, this is giving us how quickly the shock wave moves backwards. Again, I'm not going to ask you to sort of use this diagram to calculate specific things. There's a lot of modeling software that does this for us, but just so that you understand some of the fundamentals on how that modeling software works, I want you to understand that we can draw some parallels between, or some relationships between a demand, an ideal flow, and then a limited flow, and what happens when we have some relationship between those. So shock waves will occur when there's some kind of sudden reduction in capacity, so some bottleneck condition on a highway. The speeds of the vehicles have to reduce while they pass the bottleneck. So the common permanent example is a left lane ends sort of arrangement, where we've suddenly reduced the number of lanes. But typically these are placed in such a way as to not cause massive restrictions. The lanes get extended wherever they can be, so that they tend to only be lanes that tend to be dropped when they're when we've already reduced our demand to an acceptable level. But the temporary bottlenecks, those are obviously unpredictable. They can occur anywhere, and they still cause shock waves. So the point at which the speed reduction takes place, this can be approximately noted by looking at where the brake lights turn on. So if we start to see where brake lights are coming, that tells us something about, basically where the bottleneck begins, or where the shock wave begins. Now, as I mentioned before, the shock wave moves upstream. So if all the vehicles are traveling in the north direction, the shock wave actually moves backwards. It moves in the south direction. This video here is really good at explaining it, so we'll watch that shortly. Okay, hopefully that video streamed reasonably well, and you all found it quite informative. I think that diagram showing the way that the traffic snake moves is probably one of the most helpful ways of thinking about shock waves in the traffic system. And also those discussions about what makes intersections inefficient and thinking about how self-driving cars can improve them. That's also a really good topic to get your head around, a really good way to understand how in, I don't know really the times, 15, 20 years, we might see a massive shift in the way that we deal with intersections, as we're currently seeing a massive shift in the way that people deal with travel altogether. We sort of, not quite overnight, but within the space of a couple of weeks, decided that all non-essential travel did not occur. So we're not going to class at the moment. We're not going to places of work. Everyone's working from home, studying from home. Yeah, we've seen that can have some improvements to our traffic network as well. So it'll be interesting to find out how the current novel coronavirus system, or current epidemic, is going to give us some points of data to think about our changes to our traffic system in future. As always, please let me know if you have any questions, but otherwise I will press on. Now I'm conscious that we've been going for 45 minutes. I'll go a little bit longer, and then we'll take a break. How many slides have I got left? Let's discard those annotations. Yes, I'm about halfway through this first set of slides. Just to reiterate the plan for the day, so we'll have some slides, we'll take a break, we'll have some slides, we'll take a break. We'll have a lunch break, and then we'll finish up in the latter part of the day. I'm going to go through 3 topics today. So we're going to go through the the current topic talking about traffic theory and flow theory. We'll talk about gaps, gap analysis, and then we'll talk about the safe system as well. So for my Mount Helen class, you would typically be in this class until 4:30 anyway. For the Churchill campus, you would usually finish up at 1:30. We've now moved that to finishing at 2:30. If you want, you can stay around for the rest of the lecture if you've got nothing on. That's fine. Hayden will head off at that time, but I'll still be here. The alternative is you can watch the lecture in your own time once this video is recorded. So we can provide that as well. Okay, so let's get stuck into lane metering for a few more minutes and then we will take a break. So lane metering is the practice of controlling the number of vehicles that can enter a motorway. If you've been into Melbourne and you've used a ramp from a Melbourne street onto a Melbourne highway or freeway, you will have seen these signs, ramp signals on. You will have seen this arrangement with a stop line and with a discrete number of vehicles being released every 8 to 10 seconds. The actual release rate varies depending upon the capacity of the highway, but this is all done so that the vehicles on the main way can flow better. We've got an ideal flow rate. So we do this by having signals on the entry ramp, one vehicle per green signal. It's pretty straightforward. People tend to understand and behave and do what they should. The VicRoads Design Guide discusses ramp metering, and it has the following quotation in it. So citywide coordinated ramp metering, that's the official name for lane metering, CWCRM. That's the primary tool for avoiding or recovering from flow breakdown on a motorway route. It has been designed to manage traffic density on all segments of the network at sub 1 minute levels to target the delivery of maximum sustainable flow rates. So what they mean here is this is constantly monitored. We have the flow rate on the main highway that's being constantly monitored. We have the arrival rate of vehicles in the queue here is constantly monitored. And at 1 minute updates, the amount of vehicles being released is updated. So whether that flow rate changes from 7 seconds or 8 seconds or 10, it's constantly being updated so that we get the maximum sustainable flow values. Your question 9 in the key questions, what does lane metering control? We just answered that. We also have question 10, what can lane metering prevent or recover from? That was on the previous slide. So the importance of citywide controlled, what was it, CWCRM, citywide coordinated ramp metering. Citywide coordinated ramp metering is to optimize motorway safety and productivity. So we don't want people in that sort of stop-start condition. At the point where flow breaks down, that is a dangerous point. So if we can avoid the flow breakdown, we improve safety. At the same time, if we don't have a flow breakdown, we improve productivity because our overall flow rate is higher. So we've got critical arterial roads that may be at or over capacity during the peaks. So in their peak period of demand, they're not able to satisfy the amount of vehicles that want to move onto them, and they may have had relatively little additional capacity added over the years. So we have in some places in Melbourne, we've got 5-lane highways. They've been 5 lanes for a very long time, decades even, and that's partly because there's physically no space to widen the road any further. So we can't add capacity by adding lanes. We have to look at other ways of adding capacity, and so ramp metering is another really good way to do it. We've just been discussing ramp metering. Just watched a brief video on how it works. Now let's carry on with the balance of our lecture today. So our next topic is capacity and level of service. So we've talked a little bit about capacity and flow rate already, but we'll talk about how that relates to level of service and what do we mean by level of service in a few different contexts. So capacity is the maximum flow that a roadway can service at an optimum density. So we've talked about density having different effects on the flow rate of vehicles. If we increase density, we increase flow, but if we increase density further beyond a maximum, then we run into trouble and we slow back down again. So capacity is our maximum flow for optimum density. So interestingly, we always want to, as designers of roadways, we always want to make sure that we are operating below the optimum rates, because if we are at optimum density, as we discussed before, this is approaching an unstable condition. So if we are pushing up too high, we're in that area where we might be subject to suddenly and drastically increasing our delays. So we want to be operating below the optimum rate. As the demand volume increases, so the number of vehicles that want to use the road, as this increases, the vehicle interaction, so the amount of braking and turning and things that's needed between vehicles, and density also increases. So this will gradually lower the average speed and the quality of the traffic flow. And how do we talk about this quality? To measure quality of flow, we use the level of service. So level of service, we can sort of look up some definitions in road design manuals or textbooks in terms of vehicles per lane and that sort of thing. You can get these out of analysis software, so Sidra calculating the number of vehicles traveling through an intersection with signals or with a roundabout. That will also have a level of service and it will vary for different routes. So the north straight through approach on an intersection, that might have a level of service A, but the east-west straight through, that might be level of service D. So it can vary across different directions and this sort of thing. So we have a range A to F. It is qualitative, which means that we don't have precise numbers given to it. The A to F is just our sort of feel. We feel that A is very good. We feel that F is very bad. And then we have numbers in between or letters in between. And it looks at the conditions within the traffic stream, but also at the perception of road users. So we'll see, we talk a little bit more about a few other things that factor into road design, such as road safety, that not only is the real condition important, but the road user perception is very important as well. So two main measures that we use to describe the service quality of a two-lane highway are the amount of time that we spend following another vehicle and the average travel speed. So the amount of time that we're stuck behind a vehicle, this is this is extremely frustrating to drivers when they can see a posted speed limit of 100, but they are stuck at 80. It's sort of what Hayden and I were mentioning before when we talked about some roads having their speed lowered, even though they might have been operating at a assigned speed of 100 for a long period of time. One of the issues might be that it could be a route that sees a lot of caravan drivers, a lot of tourists that are traveling the route at a lower speed with a heavier vehicle or with heavier payload on their four-wheel drive or whatever they're towing with. And so the amount of time you spend following this can really give us a significant measure of that quality. We say that anyone traveling at less than 3 seconds behind the vehicle in front of them, that those are consecutive vehicles. So those are following vehicles. Obviously, the best way to improve this figure, the change in time spent following, is to provide overtaking lanes. Now the average travel speed also, this is the space mean speed of vehicles in the traffic stream. So this tells us how close to our desirable speed are we able to travel. If we are on a freeway and we're traveling at 60 or 50 or 40, then we are at a significantly lower level of service compared to our expected travel speed of 100 or 110. So we've got a few pictures here that show how level of service can be visualized. So level of service A, this is the highest quality of service that can be achieved. Motorists can travel at whatever their desired speed is. So there's lots of gaps, there's lots of ability to change lanes. Drivers are basically setting their cruise control and then they're not thinking about anything other than staying in their lane, and there's plenty of space to turn around. So as much as we've got pictures here for level of service for highways, as I mentioned before, we do also have level of service when we're talking about intersections as well. And it's basically the same thing. It's how much delay do you have versus your expectation. So in this level of service A, the need for passing other vehicles is well below the capacity for passing, so there's plenty of space for that. There are few or if any platoons, so platoons are groups of 3 or more vehicles. We don't see any sort of bunching up of vehicles, and the free flow with high speeds and this, we are below 700 vehicles per hour per lane. That's giving us this free flow condition. Level of service B, vehicles are able to maintain desired speeds, but there's some demand for passing. So as long as we have lanes for passing, this is fine. Passing is a little bit, involves a little bit of a demand on the road user's attention, so slight drop in level of service, but it's still pretty good. We're still traveling at about the same speeds as as in level of service A, and we've got quite a good capacity as well. The flow rates are starting to get a little bit higher, 700 to 1,000 vehicles per hour per lane. Level of service C, if we keep increasing our flows beyond the level of service in B, now we start to see platoons forming. So we see not only an increase in the number of platoons, but we see an increase in their size. So there's 4 here, there's another probably 4 or 5 there. It's hard to tell from the resolution of the image, but we're starting to see a larger number. The ability to pass is being decreased. You can see if you were this blue car here and you wanted to speed up and get past the cars in front, you have a significantly harder time than you did in the previous case. So that's getting, it's getting a little bit lower quality. Level of service D, now we're getting to an unstable flow. Passing maneuvers are difficult, if not impossible. The number of passing opportunities is approaching 0, but every lane is desiring more opportunity to pass. This is that scenario, and again, if you've done much highway driving in and around Melbourne, you might have often seen there's always one or two. Oh, sorry, Doug, I've just seen your question about what is a platoon. So a platoon is a group of vehicles that are following each other close together. So the best example would be, oh, thanks, Hayden. Yeah, a group of vehicles, exactly as Hayden said. You can see this is not a platoon. This is not a platoon. If we go down a bit further, we can see a platoon here. So this group is, oops, I don't know what I just did. There we go. That group is a platoon. What was that? Was that Control O? No, Control bracket? No, I don't know. I went to hit Control P for pen, but anyway. So hopefully that clears it up. So as the as I was saying before, if you're in that sort of freeway condition where the passing opportunity is really quite decreased, you might see vehicles that are trying to sort of maneuver all the time. There's always that one car you can see that changes lanes and changes lanes again and changes lanes a third time. And the vast majority of the time, if you sit in your one lane and you just go with the flow of traffic, you'll end up basically in the same position in the traffic flow as that really aggressive driver. But the difference is that person making all of those turning movements, every time they change lanes, there's a risk for an accident. And every time they change lanes, they are in 2 lanes at once. So they're actually decreasing the capacity of the road, or they're sort of they're momentarily increasing the density. So both of those reasons, you say when the traffic gets really dense, just stay in your lane. Unless you've got to get to a particular lane to exit, it really doesn't help you much, and it hurts everyone else a lot. So at level of service D, we are getting up to about the capacity. So 1,800 vehicles per hour per lane is often quoted as the sort of highest conceivable capacity for a traffic lane, and we're just about hitting that. Once we get to level of service E, we're now in that really super saturated phase. This is where a chicken crossing the road causes a big traffic snake, to use the language of our video that we saw just before. So passing has become virtually impossible. Platoons are longer and more frequent. If anything, everything's one big platoon now. The operating conditions are unstable and difficult to predict. We might be at or near 1,800 to 2,000 vehicles per hour per lane. And at level of service F, we are now at highly congested situation with demand that exceeds capacity. The volumes are lower than capacity and speeds are variable. So this is where, again, if you've been stuck in traffic, you might have seen you're traveling at 20 kilometers an hour, 10, 0, and you might sit at 0 for a minute or two, and then it opens up. Oh, you're going 20, 30, 40. You might even get back up to 60 k's an hour, and then you slow down again. And you keep doing that rubber banding between 0 and 40 or 0 and 60 for several kilometers until you break free of the traffic congestion. Please let me know in the chat if there are any questions, but I'll carry on. So here we've got some occupancy levels, density and occupancy levels, and service indicators. What are our levels of service? What are our densities in terms of passenger vehicles per kilometer per lane? So this will tell us, about how closely spaced the density is to give us different levels of service. And this tells us basically how it feels. Does it feel like free flow? Does it feel stable? Or does it feel extremely unstable with broken down and various other problems? So there are a few roadway factors that also affect level of service. So aside from just the number of vehicles that we can fit on a road, the amount of flow rate, we also have the amount of width of pavement. So the lane widths and the lateral clearances. If we have less than ideal lane widths, this also decreases our level of service because it decreases the comfort of the road user and how comfortable they are operating at the signed speed limit. So if you ask someone to drive at 100 kilometers an hour in a 3 meter wide lane, they'll feel pretty uncomfortable. I might have mentioned before that typically a lane on a highway is 3.5 meters, and anywhere else that we can fit a 3.5 meter lane, that's the standard for the state and across Australia. We try to fit 3.5 meter lanes. Notably, the Westgate Bridge, the Westgate Bridge has 3 meter lanes, so the speed limit is decreased there, but you might have always noticed that you feel a bit anxious on the Westgate Bridge, and maybe you didn't know why. The next time you drive over, have a look at the lanes, and this might explain to you why you feel like that. Shoulders also, so this is an area, for those who don't know, a shoulder is the area which is outside of the part of the pavement that you're meant to drive on. It's this sort of part over here that is available if you make a mistake. It's sort of a correction space. It's a space to pull over if you have a breakdown. So this is an unsealed shoulder, and we also have a bit of an edge break between the main sealed part of the road and the unsealed shoulder. Both of these factors would be what we would describe as a less than adequate shoulder. So this will also tend to decrease road user comfort and decrease the speed that they're happy to travel. Poor surface conditions such as waving, rutted, or otherwise deteriorating road, an alignment that is less than desirable. So if we've got a road with lots of curves and the curves are not of a suitable width or a suitable radius, this would also give us a lower level of service, as do poor or severe grades. So the grade is the vertical change in the road. On a highway, the most I think, ever want to have is 7%, and 6% is desirable. The 6% doesn't sound like much. There are lots of parts on the Western Highway where if you're coming from Melbourne, you're climbing up a hill consistently at 6% for kilometers because you need to climb, 6% over a kilometer distance only gets you 60 meters, and Ballarat is in an elevation of 400 meters. So there's some sections there where you've got to climb up quite a bit. But there is, to change it only a little bit, the Midland Highway from Buninyong to Geelong, just as you're leaving Buninyong, there is a section at 7%, and that causes quite a number of truck breakdowns each year because that trucks go through the roundabout, they're starting from a stop in Buninyong, and then they have to try and pick up speed at a 7% grade, and they can't do it. So 6% is our desirable grade. Anything higher than that, again, will decrease our capacity and our level of service. Another thing that can affect this level of service is traffic factors. So the number of trucks, buses, and the presence of vehicles in different lanes. This can also change things. So as we mentioned before, trucks will move a bit more slowly, especially on an uphill grade, as do buses. They tend to be traveling a bit slower. It's not too bad now in 2020. A lot of the buses and trucks that we have are really good, strong engined, way more powerful and have with way more torque and things than they did in the past. But going back 20, 30 years, a truck would really struggle. If you were out on the Western Highway, you wouldn't be stuck behind a truck doing 80. The truck would be doing 40 or less. They would really struggle, but they've improved quite a lot. And we also can talk about variations in traffic flow. So if we have an intersection that's just before a highway that's releasing big chunks of vehicles, this will be a variation in the amount of vehicles that are sort of coming in, and other interruptions to traffic, like the presence of intersections or other requirements to slow and stop. We might talk about roadworks and the slowing down of vehicles to drive past the roadwork section. Again, these are all the different characteristics that can change the perception of a road. Let me just quickly check the questions that we've got. So we've got here our questions 11, 12, and 13 have come up recently. How is the capacity of a road defined? That was just the start of this section. Question 12, what does the level of service describe in the context of traffic observation? So that was shortly after the start of this section. Pardon me. And what is the capacity of a highway under ideal conditions? We had that up on just a few slides ago as well. So the service flow rate, this is defined as the maximum hourly rate at which persons or vehicles can be reasonably expected to traverse a point during a given time period while maintaining a designed level of service. So this is the service flow rate for service A, B, C, D, would all be different. We have those different values like what we saw recently. Once we get down to level of service F, then we're in this stop-start arrangement. So it's not really meaningful to talk about a service flow rate because it is so irregular at that point. And at each level of service, the service flow rate is defined as the maximum for that level. Now, we've got a few ways of determining capacity and service flow rates. So one of the things that we need to do is first determine whether the flow is interrupted or uninterrupted. And if we have an interrupted flow, then we're going to need to make sure that we are accounting for the presence of those intersections and give-way signs and traffic lights. If the flow is uninterrupted, then we'll use a different kind of modeling to work out what the capacity and service flow rates are. We can divide the road into subsections which have reasonably uniform conditions. So sections with the same number of lanes, the same lane width, and the same speed limit. We can divide it up into this. We can identify critical bottlenecks, and then we can perform some sort of traffic survey, some speed studies or volume studies to see exactly how vehicles are operating in that area. So this is our answer to question 13. What is the capacity of a highway under ideal conditions? We have, under ideal conditions, we have for a two-lane, two-way road, 2,800 vehicles per hour. This is the total for both directions. And these ideal conditions give us at least 100 kilometers an hour, a lane width of 3.5 meters. We want clear shoulders. When I say clear shoulders, I mean we need space that is at least 2 meters wide with nothing in them. No signs, no trees, no potholes. The shoulders need to be at least 2 meters wide. We want to have long sight distances. We want mostly passenger cars or only passenger cars. And we want a 50-50 directional split in traffic. If we've got all of these conditions, we're relatively flat, we've got no turning controls on vehicles, then under those ideal conditions, we can have 2,800 vehicles per hour. And everything that we change, if we lower the speed limit, if we lower the presence of shoulders, if we have narrower lanes, or if we have 60-40 traffic, all of this comes down. This formula, I've left it in because it's like you might see it pop up in future in textbooks or in any calculations you're asked to do. We're not going to use it particularly, but one of the ways that this would be broken down, if we wanted to talk about the particular level of service flow rates for different rates here, so SFI, service flow rate A, B, C, D, E, we would take that as 2,800 times volume divided by capacity of A, B, C, D, E. So we would see, if we're increasing the overall capacity value compared to the volume, that this number is coming down. And then we just have factors for the presence of heavy vehicles, factors for the road width, factors for the directional distribution of traffic. So again, if you were reading this out of a design standard, you might have a table that displayed the lane widths, and maybe a 3 meter wide lane has a 0.9 factor, just to make up a number. But that's the kind of thing that we would see here for figuring out capacity. I don't think it's particularly useful. I just wanted to bring your attention to, or not particularly important for you to know off the top of your head, but I just wanted to bring your attention to the idea that these things do exist, and if you are designing highways from scratch, you can use this as a tool to make some predictions. we've got the heavy vehicle factor here, which, to be honest, I probably should have deleted this slide. We can factor in the amount of trucks and buses. We can look at, you might see here that if in the square brackets everything is on the bottom, and we're taking away we're sort of multiplying the total percentage of trucks, the total percentage of buses. We're having a number in the denominator of this expression which is greater than 1, so the heavy vehicle factor is always going to be less than 1. As we increase trucks and buses, we're going to see a decrease in the overall level of service that we can provide for the same flow rate, or rather the decrease in the flow rate for the same level of service. But not particularly fussed about that. And if we were to have a couple of other things that we could look at, we could have an adjustment factor for a driver population as well. So we can see that if you had an aging population, as you do in particular parts of the state, or Florida comes to mind in America as a place that has a historically or well-known aging and inexperienced driver population. We can have other factors for presence of shoulders and this sort of thing. Basically, it breaks down to one condition of a flow rate number, a ratio between your demand and your capacity, and some factors that then decrease that value. Okay, just a quick look at one of the worst traffic jams that happened in Russia. I don't exactly know the history of this one, but just from the picture you can tell there that that's not going to be a very nice place to be for anyone. Let's make sure I'm picking up the right slide. Yep. So this next lecture we're talking about queuing, gap acceptance. We're also going to be talking about the design of intersections. So just some intersection basics. That is to say, not doing the full three-dimensional design. We're just going to be looking at the two-dimensional layout for typical intersections. We'll also look a little bit about stop-give-way conditions. We'll look at what is a BAL, what is a CHR, so it's a basic auxiliary left turn or channelized right turn design, and some of the other just general theory that goes into this. So, in gap acceptance, and if you check your key questions, your first 3 questions are on this slide and the next 2 slides. Some important measures or some important things to discuss in the gap acceptance concept are first up, merging. So we define a merge as the process by which a vehicle in one traffic stream joins another traffic stream in the same direction. So this is a classic example where we have a traffic ramp, an entry ramp, and we have a traffic stream over here with 4 lanes of vehicles. This is a merge between the ramp lane vehicles and the other 4 lanes. The outer lane doesn't look like it's being used. Maybe that's a carpool lane or something. But in any case, this is a merge, and that's typically how we define it. It's one stream that joins another stream in the same direction. A diverge is the opposite. So this is the process by which a vehicle in a traffic stream leaves the traffic stream. So here we have a 2-lane highway. There would have been an exiting left turn lane, and so the vehicle's been able to leave there. So this is just a typical sort of exit signage. That's a diverge. It's reasonably straightforward. We usually will have some kind of lanes, especially in a highway environment, that help to facilitate the diverge and make it safe. Now, weaving is another concept that we'll discuss. It's the third of these 3 important concepts, and it is there's important things to note about weaving. So weaving is the process by which a vehicle first merges into a stream, and then they have to cross that traffic stream to merge into a second traffic stream. So I've highlighted an area here, the Westgate Freeway in South Melbourne. So if you've come over the Westgate Bridge, for anyone who's done this part of the drive, you'll know if you come over the Westgate Bridge, you'll then come into a section of road where there's lots of ramps that depositing traffic on the left and the right of you. There's merging streams, all of this stuff here, and then there's exits to Kingsway, Montague Street, Power Street, or heading to the bridge. And wherever you are, wherever you come in on this route, if you want to get to your destination, you typically have to weave. You have to change lanes in some way in a very busy, congested part of traffic. And again, I want to point out, if for anyone who's done this drive, that you might have felt, somewhat uncomfortable. You don't have a really long length to figure out what lane you need to be in to get into that lane, to try and pick a gap in traffic when everything's so congested. And I wanted to point that out because weaving is a dangerous maneuver. Anytime we change lanes in general, it's dangerous. This is why the Westgate Bridge has signs that tell you to avoid a lane change. And in the tunnels, they explicitly tell you all the time, avoid lane change is flashed overhead in the tunnels, because weaving is dangerous. And if you're forcing vehicles, or rather lane changes are dangerous, but if you're forcing vehicles to change lanes because of the way that the road is arranged in terms of the need to weave from left to right, the safest thing to do is to use this concept called ramp braiding. So you can see the left side of this picture, there is a ramp and it twists over this lane here. So rather than have these three lanes, the people in the outer left lane have to sort of merge and then merge again. We use this ramp braiding arrangement to deposit vehicles safely over another traffic stream. It works very well, but it's very expensive. You might imagine that this section of bridge, I'm not sure what you think it costs, but probably add another zero to it. I would say it would be in the order of $20 or $30 million worth of bridge structure just in here. So they're very expensive to do, but considering the volumes of vehicles that use this part of the highway in Melbourne every day, the safety benefits are really there, the capacity benefits are there, and so the structure gets built. Okay, so another typical definition in gap acceptance, or critical definition in gap acceptance, is the definition of a gap. So what do we mean by a gap? This is the headway in a major stream, which is evaluated by a vehicle in a minor stream who wants to merge. So here is the waiting vehicle. Down here, he's looking to either merge into the stream or to cross the stream or to make some sort of movement. And so we define the gap as here. This is the gap between the vehicle that's waiting and the approaching vehicle. And we can define this as a time gap or as a distance gap. Either way, we can perform then some calculations and figure out whether this gap is acceptable and what the driver is going to do with it. Another concept is time lag. So this is the difference between the time that a vehicle merges into the main traffic stream and reaches a point. So this vehicle's merged, they've moved in, say here, and the time that a vehicle in the mainstream reaches the same point. So it's how long does it take the following vehicle to reach the same point after the merging vehicle has entered. This is the time lag. Another way you can think about gaps in traffic and merging. Space lag is the same concept, but instead of talking about time, we're talking about distance. Again, we're basically just looking at how many meters between versus how many seconds between entering vehicles. Okay, on this graph, what you can see is a distance on the vertical axis and time on the horizontal axis. So a distance versus time graph. This is basically showing like velocity. The gradient of these lines is showing velocity, and the fact that we are starting from different origins, not starting always from 0, 0. This tells us that the vehicles are separated in space as they move along. So if we can see vehicles traveling at the same speed close together, these are the vehicles on the main stream. They have gaps between them where another vehicle might try to enter. But these gaps are too small. So there's a stop sign here, we've got a vehicle waiting to enter. The distance doesn't change as the time changes. So basically this vehicle's not moving. It's staying steady as time increases until it sees this platoon of 4 vehicles passes, and there's a large gap between the last vehicle in the platoon and the next vehicle behind it. So this vehicle can enter the stream. It wouldn't really be suddenly kinked like that. This would be an instantaneous acceleration, or an infinite acceleration, which we obviously can't physically have. It should be a curve, but anyway, this vehicle is able to enter the traffic stream, and it's able to do so because of the gap, and also because it looks like this vehicle here is traveling slower than the others. So I would potentially even say you could get to about there, or here, or thereabouts, if this pink line was traveling at the same gradient as the others, and then the pink line might slow down. So if you see a vehicle enter, you've probably noticed this yourself, you see a vehicle enter a traffic stream, you can just take your foot off the accelerator and help them to get in safely. Every now and again, you might recall merging into a traffic stream, and for whatever reason, the person behind you really makes it necessary to come right up to right up to behind your vehicle in a really aggressive and obnoxious fashion. I don't know what benefit they hope to gain out of that, but you'll see it happen from time to time. So this diagram basically just shows what a gap looks like and how vehicles get into it. Now, gap acceptance is the name of the game today, or the name of the game for this topic. So gap acceptance is telling us what drivers reject and what they accept in terms of their safety and in terms of the physical space that they want to put their vehicle into. So a driver who intends to merge must first evaluate the gaps. They need to look at the gaps. They need to assess the gaps based on a sort of a risk-reward proposition. You know, if you're looking at gaps in slow-moving 10 or 20 kilometer an hour traffic, that's the sort of speed environment where sometimes people just push in. But if you're looking at gaps in a 100 kilometer an hour environment, people need to seriously weigh up, okay, how quickly can I accelerate? Am I going uphill? Is that vehicle going to see me? Is the gap big enough that I can get up to speed before I get in there? So is the gap large enough? That's going to be a critical factor. In accepting the gap, the driver will complete a merge maneuver. So they will merge and get into the gap and safely join the traffic stream. So we refer to this phenomenon of evaluating a gap after wanting to merge and then performing the merge as gap acceptance. So gap acceptance is important for engineers who are trying to consider delay of vehicles on minor roads that want to join the major road. So we also want to know about delay of ramp vehicles that want to join expressways. We've got concepts of the first vehicle in a gap, a second vehicle, follow-up vehicles. All of these terms we need to define in some way, and you'll see shortly that it's quite easy to define. And this will tell us how the vehicles will actually move into place. Your question 2 for the key lecture questions today is explain the term gap acceptance. So hopefully you're able to do so after reading this slide. So we have some Australian standards that give us gap times. We have critical gap acceptance time, or critical acceptance gap time. We have a follow-up gap time as well. So this term TA, this is the size of a gap in seconds that a driver needs to make a maneuver. And the follow-up gap time, this is the additional time that subsequent drivers need to make the same maneuver. So again, to try to describe this, you're sitting at a stop sign and you want to enter a stream of traffic, and your friend is sitting behind you. So TA, that's the time gap that you need to get into traffic, and TF is the time that your friend needs after they see you make the same maneuver. If you're not carpooling, but if you're making a bit of a road convoy, taking two vehicles to the same destination, and you don't want to be separated, you should look for a gap that's big enough for you and for your friend. So for TA plus TF. And we can see there are some tables of gap times given in the Australian Guide to Road Design Part 4A. So this is that table here. We can see there are different gaps sizes for different turns, so a left-hand turn, a crossing maneuver, a right-hand turn into or out of a maneuver, and we have different size gaps for the acceptance and the follow-up gap time, and these change depending upon the traffic conditions. So do we have multiple lanes? Do we have an entry which does not interfere with oncoming traffic or which requires oncoming traffic to slow? What sort of presence of acceleration lanes are there? That sort of thing. So we've got another question for you. In question 3, what is the difference between the critical acceptance gap time and the follow-up gap time? So that was defined on the last slide. And question 4, what is the critical acceptance gap time to cross a 2-lane/2-way traffic stream? So you might be able to see in here we have a 2-way, 2-lane, 2-lane 1-way, where is it? 2-lane 2-way traffic stream, and we are crossing. So we should be able to see that the critical acceptance gap time, this is that here, it's this one, 5 seconds. Please let me know if you have any questions, but I'll move on. Okay, gap acceptance theory looks at some kind of distribution in vehicles that are approaching a particular point. So we can look at, we can use gap analysis to determine the delay of minor stream vehicles that want to enter a major stream. And the way we do this is we consider the traffic flow on the highway to be essentially randomly distributed. So we say, well, we don't exactly know when vehicles are arriving or departing from a particular point. If they're on a highway or a freeway, they're not going to be subject to traffic conditions that will tend to bunch them up. They will have traffic conditions which will just have spread them out over their travel distance. So they'll be randomly distributed. Now, if we want to look at the mathematics of putting one gap or trying to find a gap in a randomly distributed stream of traffic, we can use a probabilistic approach. We can make some calculations with the natural exponent and natural logarithm, similar to what we've shown below. So this is called a Poisson distribution. Now, I'm not going to expect you to use this formula. I just want to show it to you so we can point out a few things about it. Basically, the number of vehicles increasing will give us a larger probability of vehicles arriving at a given time. And we have a distribution that is it's going to become quite heavy because it's to the power of n. So this is n vehicles arriving, even though we're dividing by n as well. Because we're raising to the power of n, we tend to find that above a certain saturation, there's basically no gaps. The probability of n vehicles arriving in time t is really very high. So this is how we could do the calculation manually, but what tends to happen is if you need to analyze the ability to get into, for a minor stream vehicle to get into a major stream of traffic, you will put in numbers into analysis software. The software will make these calculations in the background, and they will give you an answer and tell you how many vehicles are able to enter that traffic stream. So that's why I don't expect you to use this formula or know how to use it. Just want to briefly touch on the fact that should you ever do a dissertation, or if you want to design any calculation software yourself, you might start looking at Poisson distribution. But in general, the calculation software that exists for engineering designs, they're pretty good, and they take all the hard work out of it for you. So let's not make things harder than they have to be. So, and this is basically just reiterating what I just said. As analysis of gaps and delays are completed with computer packages such as Sidra, we will not focus on manual calculation of gaps in this class. So yeah, all of this stuff, you'd basically just set it up in software and you'd go from there. Okay, I might go for another, actually no, I'll go for 15 minutes and then we'll take our half-hour break between 12:30 and 1. So let's get into our next topic, which is queuing. One of the greatest things that we need to worry about as traffic engineers is congestion existing on urban highways, especially during peak hours, and largely this formation of queues is our biggest issue. So we'll show a couple of ways we can make some calculations on the size of queues and the economic cost of queues coming up. So we can either look at a sort of a deterministic approach or a stochastic approach. To be honest, I don't actually know what the term stochastic means, which I'll quickly Google now. I think I did look it up. Oh yeah, this is randomly distributed. Yeah, I did look it up. So so we're either saying that we can assume that we have an exact characteristic of traffic flows, or that we can make that randomly distributed assumption that we just talked about on the last couple of slides. So if we take a deterministic analysis, we're basically saying that all characteristics of the queue are known. So we know volumes, we know capacities, we know demand, and this will let us make some calculations. There are two common traffic conditions where we might use this approach. So we would have a varying service rate and a constant demand. So basically we're constantly injecting the same number of vehicles into a traffic stream, and our level of service changes based on how that constant demand moves along highways with a different overall capacity. So if we have a significant reduction on the capacity of the highway, this will give us a big change in the level of service or the service rate. We can also have varying demand and constant service rate. If we were to have the ability to control the demand, such as with lane metering, we can try to provide a constant higher service. Okay, so we're going to talk about some light calculation. We're going to see some graphs of how service rate and constant demand work, and we'll get you to do some manual calculations on this. So we've got some tutorial questions that are available in the week 4 material. Now the reason that I am going to ask you to do some calculations in this area is because I think they're pretty straightforward, and they can help you to if you were asked to calculate what is the cost to the state of a particular traffic queue forming, it would enable you to very quickly work it out. So that's what I'm going to get you to a little bit later, but we'll build up to that over the next couple of slides. As always, I'm not seeing many questions in the chat, but please just let me know if you have any questions there. So if we consider a section of 3-lane, one-direction highway, a capacity might be C vehicles per hour. So now we have this hypothetical situation. So we had a capacity of C. Now we have an incident, so some truck rollover or something, that's given us a closure of one lane. So the capacity has become CR. This is the reduced capacity for a period of T hours. So the time taken to clear the incident is T. The starting capacity is C. The reduced capacity is CR. The demand volume remains constant over this time. And the demand volume, V, is greater than the reduced capacity, but less than the starting capacity. So now we ask, how can we determine the maximum queue length, the duration of the queue, the average queue length, and the time that a driver spends in the queue? How can we determine the average queue length while the queue exists, and the maximum individual delay and the total delay? So there's a number of things we can find out about this queue with reasonably straightforward math. And it will, as I said before, it will then allow us to if we were in a position to, if we were working for a local council or for a state government or something like that, we would be able to determine what the actual financial impact is of these delays, what the level of service delays are, and make some assessments out of that as well. So this is what the graph looks like. On the vertical axis, we have flow rate in vehicles per hour. On the horizontal axis, we have time. So our dotted line, this is the capacity of the highway, and it changes before and after the incident. So before the incident, we've got capacity C. During the incident, the capacity drops to CR, and then after the incident, the capacity returns to C again. The whole time we have a constant demand. Now, the smarter ones among you will probably already have noticed that we have an area shaded under the graph here, or if I were to do this, I could say I'll shade this area here. And we could find that if we found the area under this graph, we would find the number of vehicles. So we could use this as one measure pretty quickly to find out what's going to happen. But there's another way we can graph this information to find out even more about more characteristics about the flow. So on this graph, we have cumulative vehicles on the vertical axis, and we have time on the horizontal axis. So again, we have an incident that lasts for time T, and the cumulative vehicles is increasing linearly because the V, this value V, the demand, hasn't changed. So this stays the same. Now, in addition to the time, the incident having a certain time, the incident also has a certain reduced flow rate. So this is vehicles per time. That's the rate here, the clearance capacity CR. This is how quickly we are able to get vehicles out during the incident. And then once the incident finishes, this slope here, this is how quickly we are able to get vehicles out once we return to the flow rate C. So again, we have an area under the graph here an area between the line of V and the line of CR and C that tells us how many vehicles total were in the queue. We can see how many vehicles are in the queue instantaneously by looking at the height of these lines. And we can see what the total duration of the queue is by looking not only at the time of the incident, but how long it takes for the line at gradient C to catch up with the line at gradient V. So looking again at this formula, at this graph, we're able to surmise just a few basic geometry formulas, looking, the areas of the different triangles on here, and we can work out how to calculate the time for the total queue to clear, the delay to an individual driver in the queue, and so on. So here are a few quick queue length formulas, and we've got these as your key lecture questions 5. So question 5, A, B, C, D, these are asking you to write down what these formulas are, because I will ask you to use those in the tutorial, and I'll probably have an exam question on them as well. I don't think they're too complicated, but I think they're quite useful for you to know. So the maximum queue length, this is the excess demand rate, so how much higher is the demand rate than the reduced capacity rate, multiplied by the duration of the incident. This tells us what is the maximum queue length. Again, pretty straightforward. You can see that if we have on the previous slide, if we have a difference between these two gradients and we have a time, we can basically perform the mathematical operation shown on the last slide to find the height here. We can also see the time duration of the queue length divided by the difference between the capacity and the demand rate. So we have capacity minus the reduced capacity multiplied by the time of the incident, and we divide that by the total capacity minus the demand rate. So we're saying in here that we have an ability to clear the vehicles. This C minus V, this is how much extra capacity we have other than the new vehicles that are being added onto the queues. This is how quick the queue is clearing. And this up here, this is how quick the queue was forming. So just to go back to the previous slide again, we can see this is the queue forming, this is the queue clearing. Both of these figures relate to V, and they relate to the total time, and that's what you can see in there. We also have the average queue length. This is simply the total queue divided by 2, so Q max divided by 2, pretty straightforward there. Now the total delay, this looks a little bit fancier or a little bit heavier, but if you've calculated this in the previous steps, it's actually pretty easy. So the total delay is the time duration of the queue multiplied by the average queue length. So we have here the time duration of the queue, and we have the average queue length. If you've already calculated this, and you've already calculated this, you can just multiply them together. Or if you're calculating them from scratch, then you can use this formula. But either way, it's the same. The most important thing is to ensure that we put the same units in for all variables. So if V is in vehicles per hour, CR needs to be vehicles per hour, C needs to be vehicles per hour, T needs to be in hours, that sort of thing. This would work fine if you use vehicles per second and total time of seconds, or vehicles per day and total time of days. As long as you use consistent units, you will get an answer that makes sense. But your answer will come out, dt, the total delay in time, dt will come out in whatever time units you put in. So if you put hours in, you'll get hours out. Hope that all makes sense. Please let me know if there are any questions. As I said, we'll have some tutorial questions on those, which we will go through in an upcoming tutorial session. All right, a little bit longer and then we'll take a break. How much longer have I got until the next break? Yeah, I've got a few more slides to go through and then we'll take a break. So varying demand, constant service rate. So if we have a demand that looks like this, because we've got a morning peak and an afternoon peak, vertical axis is our total traffic, horizontal axis is our time through the day. We can work out, if we use the above described method, so if we use the calculation tools that we've been previously talking about, we can make some assumptions about the demand changing at specific times, so not having a gradual increase, but about lumping together into specific time groups, and then we are able to make some calculations based on that. So even though our true demand rate is curvilinear, we can make it into a block shape, and then we can use the calculations we've just been talking about. So stochastic analysis, this random analysis of queues, considers the fact that certain traffic characteristics, such as arrival rates, we can't really determine. It is somewhat randomized. If we have light to medium traffic, the arrival rates tend to be quite random. Once we get to a very high density, it's reasonably uniform, but until that point, light to medium traffic, we have a sort of a random distribution. So the stochastic approach is used to determine the probability that an arrival will be delayed. It can be used to determine the expected waiting time for all arrivals, the expected waiting time for an arrival that waits, and so on. So this is one of the principles that we use to determine queue lengths in computer modeling software. Again, I'm not going to ask you to do this part of things because this is significantly more difficult to calculate, and because the modeling software is going to be what you will use, not even 9 times out of 10. You will use this 10 out of 10 times if you are asked to do any kind of full calculation. This stuff back here, you could do what I would refer to as a back of the envelope calculation. If you were in a meeting, you were talking about delay, and someone said, "Oh, well, how much is it actually costing?" This is the kind of thing you could realistically calculate by hand on short notice and get a meaningful answer. This one is, you're going to go to a computer modeling every time. So we have some short queues that will form when we have an arrival that waits for a gap or an opportunity. So here we have a waiting right turn. We're in Melbourne, so it's a hook turn for the tram lines that we're crossing over. And you can see there's a number of vehicles that are able to fit in here before the other vehicles that can go past. Now we have queue generations at demands for turning. We have queue generations at tolls for toll booths or parking garages. Anywhere that there's some sort of need to stop and wait for something and a demand for vehicles using that area, we're going to see a queue form. We have a relationship between the expected number of units in a system, so the expected number of vehicles, and the ratio of the rate of arrival to the rate of service. So what we're seeing on this vertical axis here, this is the expected number of vehicles in the system, and this is our traffic intensity as a ratio of flow rate divided by capacity. Now, we can't have a flow rate that's greater than capacity, so 1 is the maximum intensity we could have, a flow rate that's equal to capacity. And at that point, we would see the number of vehicles in a queue basically being infinitely high. Where we've got a flow rate to capacity ratio that's very low, up to about a half a unit, we'd never really have more than 1 vehicle. But what I'm hoping you're able to see and understand about this curve is that as we increase, small increases in the flow rate demand divided by the flow rate capacity, we get a very steep increase in the probable number of vehicles in the system. So queuing is of no significance when our intensity is less than 0.5, but at values of 0.75 intensity and above, the average queue will increase very quickly. As we approach 1, we get very quick increases in traffic intensity. Back into our discussion. So the next part of our topic, talking about gaps and queuing, is talking about BAL and CHR standards. So this is basically left turn and right turn lanes and how we go about designing them. So we have this concept called turning lane warrants. And this basically is a standard way of defining when turning lanes are going to be needed. So that whether you are in, if you're in Victoria or you're in New South Wales, whether you are building a housing development or you are building a new Bunnings warehouse or something like that, who decides what the turning lanes should be? How do we make sure it's consistent? So these turning lane warrants, they're given in section 2.3.6 in the Austroads Guide to Traffic Management, Part 6. And they basically tell us what basic auxiliary, channelized turn treatments or other treatments need to be provided for different layouts. I think we've got a tutorial question based on this. So, yep, so question 6, where can turning lane warrants be found in the Austroads guides? That's section 2.3.6. I think that's important for you to know because whether you are in private development, in government, or whether you are, you know, in a planning space, or if you're in a design space, you're probably going to need to know where these tables are. So that's why I thought I'd make sure that you remember that. So the major factor for the turning lane warrants are the volumes of vehicles on the minor and major roads. You'll see that's basically what it comes down to. How many vehicles are on the major roads, how many vehicles are on the minor roads, and what direction do they need to turn in. That's basically all that we need to look at. There's a few other considerations, but that's the biggest part of it. So as part of a traffic generating development, the Road Management Authority, so that could be Vic roads if it's an arterial road, or it could be the City of Ballarat or the City of Yarra or any kind of local council if it's a local road, they can require the construction of an appropriate turning lane for vehicle safety. So you want to build a Bunnings or you want to build a subdivision, some development that generates traffic, that's what you want to build. The Road Management Authority can make you construct an appropriate turning lane. Now, the turning lane warrants, so exactly what is judged as appropriate here, this depends on the turning lane warrants. So those warrants, in addition to looking at the minor and major road volumes, they also look at factors such as the steepness of the grade and the sight line distance where the lane will be constructed. So basically, are we heading down a steep hill or heading up a steep hill? Is there adequate sight distance? Are we on a straight road? Are there trees that block sight lines? Are we on a bend? All those kind of things need to be considered. So this figure explains how the values are to be calculated when we're trying to work out this key term QM. So QM is the major road traffic volume. The major road traffic volume. And that is whatever is going to be flowing. It's going to be one of the axes on the graphs on the following page. The other axis that we need to worry about is our particular turn movement. So whether it's QR for a right turn in or QL, that might be what we need to look at. But in general, you can see we've got this value QT1, so that's, say, your eastbound traffic. QT2 is your westbound traffic. And then we make up QM, that's the value of the major stream traffic, depending on what we're doing. Is it a two-way road? Are we turning right or left? Is there a splitter island? This tells us basically just the simple sum of some of these other terms. That tells us what we need to be looking at. And here are the warrants themselves. So there are 3 diagrams that look basically the same as this, and they change with speed limit. So we've got one that's 100 kilometers an hour, one that's 70 to 100, and one that's less than 70. And basically what they have on their vertical axis, they have the turning volume in vehicles per hour, and this is the vehicle volumes that we are adding. So what your traffic generating or traffic demand generating development, that's going to produce a demand on this axis, and then your major road, that has a result on this axis. You basically read up the 2 points, and you find out where you sit. So if you're on this side of the red line, then you've got the cheapest treatment that you need to make. You need to either build a basic auxiliary left or a basic auxiliary right treatment. We'll see what the geometry of these is in a bit. If you're in between the blue and the red lines, you need to make a channelized right turn short, the S stands for short, or an auxiliary left turn short. And then if you are even longer again, you'll need to make a channelized right or a channelized left or an auxiliary left at full length. So that's basically how these diagrams work. As I said, there are 3 of them, and I think we have another tutorial question for this, another key lecture question. So one question is question 9, what does the C in CHR stand for? And what does the S in CHRS stand for? Which I think is on... I did say it a few times, but it's going to be coming up in another slide anyway. So here are the turning lane warrants. You can see they vary slightly. This has got up to 80. We can, in a lower speed environment, we can have more vehicle movements coming in. And again, we come down lower again, we can have more vehicle movements coming in and more vehicle movements on the major road, which just makes sense. we don't need to worry so much about the potential risk. Obviously, we need to make sure that things are still safe, but the safety is going to be easier to achieve in lower speed limits. Okay, do let me know if you have any questions, but hopefully so far that's pretty straightforward. So once the appropriate turning lane arrangement has been determined, what does the S stand for? So the S stands for short. If I go here, we've got CHRS, which is a short lane type. And if I go back one or forward one, so we've got CHR, which is channelized right turn treatment. CHRS here, channelized right turn treatment, short lane type. It's basically just a slightly cheaper version of the same thing. Okay, so in terms of our turning lane geometry, we need to first decide what treatment we need. Is it a BAL? Is it a CHR? That sort of thing. You're welcome. Once we've determined the turning lane arrangement type, then we need to start to design the intersection. So the geometry, lane lengths, widths, and so on, these can be read from the Ostroads Guide to Road Design, Part 4A. So that this guide gives us information on geometry for right turn treatments in Section 7, and Section 8 gives us geometry for left turn treatments. I'm not sure if I've mentioned this before, but all of these Ostroads guides, whoops, what did I just do? Didn't mean to do that, sorry. All of these Ostroads guides, they are all available online for free. You used to have to pay for them, but they have now become free for anyone, which is really good, especially for students. You basically just need to log onto their site and you can get a PDF for nothing. If you want to get a physical copy, you still need to pay for it, but the PDFs are free. So if I'm directing you to look up these guides as part of an assignment or anything, you'll be able to look that up without much worry. So in our turning lane geometry, we have, starting in Section 7, we've got the simplest right turn treatment. So the simplest right turn treatment is a BAR, a basic right turn, a basic auxiliary right turn. So you can see here, this is the sort of the layout of the lanes. We've got an eastbound lane or westbound lane and an eastbound lane. The lane lines stay basically where we are. All we do in this treatment is we just build a little bit more pavement out on this side, just a little bit more. So that if I want to turn in here, my vehicle can stop in this position here, or thereabouts, and I can wait, actually probably more further back would be better, but anyway, you stop basically there and then you turn in. I'm not sure why that line is stretching, but it doesn't matter. Oh, I drew it in completely the wrong spot. Hang on, let me see if I can erase these. Yeah, I can. Sorry, let's try that again. So we should really be more like this, and I wait to turn in this way. Again, I'm really not sure why that's happening. We wait to turn in this way, and while we're waiting, vehicles are able to do this around us. That's all that the auxiliary right turn treatment is there for. It's basically just a bit of extra room to move around, and it's reasonably cheap construction. You don't have to do a lot to make this happen. It's just a bit of extra shoulder widening, really. Now these lengths, the A, the S, the X, the W, these are all defined in this section. So if you went to section 7.5.1 in Ostroads Guide to Road Design Part 4A, you would see definitions of A, S, and X underneath, and the definition of C, and then you can basically just calculate how long these things need to be. So S is a function of storage, X is a function of the vehicle turning width, so what's the design vehicle and how wide does the design vehicle need to turn, and A is a function of how wide we are moving off the main road and what is the speed environment. So how comfortably can we make this turn here, and how comfortably can we make that turn there? That tells us A. The next next level of intensity for a channelized turn treatment, channelized right turn treatment, is a CHRS. So it's, as it says here, more desirable than BAR. It's CHR, but it also costs more to build. So you can see there's a little bit more complication in the diagram here, but all of these figures, the D, the S, the T, the E, they all define the overall geometry, and they do it in a uniform way so that you have this benefit that if someone wants to develop, again, if someone wants to develop a McDonald's or a Bunnings or something, and they know where they want to put it, the developer typically will go to their engineering designer or their planner, and they'll say, "Oh, roughly how much is this going to cost me?" And they don't have anything except that I want to build a Bunnings, and I know where I want to put it and how much is it going to cost. And this diagram immediately tells you, once you know how to read it, basically how long and how wide the pavement is going to need to be, so you can get an idea on the cost and decide if you want to proceed with the development. If that decision is made and the developer does proceed with the design, then this becomes a common point of reference between the designer that works for the developer and between the council or the state government. So the council officer isn't saying, "Oh, I want the design lane to be 100 meters long or 150 meters or no, 200 meters. I feel like 200 meters is the right number." All of this is defined in the standards, so everyone's talking the same language. No one's pulling numbers out of the air. It's all based on good, calculated, proper engineering. So some of the features that you can see here is, unlike in the previous case where basically the right turn lane stayed in the main through lane and vehicles were expected to just drive around when someone slows down, now we have the situation where the person turning right or the vehicle turning right actually has to depart. So we have this chevron marking, this painted island, so people will come around the island, then they'll queue in here, and the road is telling vehicles that approach to go around whether or not there is someone waiting. Now we have a more intense form than this, and that is an urban channelized right turn treatment. So this one, we have a full separated median, and from the in adjacent to the through lane, we must turn into that right median and then make our turn movements. The words urban and basic and that sort of thing, it doesn't necessarily have to be in an urban environment, because the main trigger, as we mentioned before, comes from the traffic volumes. So if the traffic volumes are there, then ideally we should still be building something that is nice and robust like this. There are some right turn treatments which are built in a similar manner to this on the Western Highway near, what's the place called? It's west of Ballarat, west of Miners Rest. Can't picture it right now, but basically there's some right turn treatments that look like this, and they're definitely not urban. It's not an urban environment, but that's just the language used to define or to describe this treatment. Okay, so now we'll get on to the left turn treatments. So as I said in section 8, we have left turn treatments as well. So this first one, the BAL, it's very similar to the BAR in that we basically just have a bit of extra pavement here. There's no extra line marking. The through pavement is still shown like this, but this place gives people extra space to pull over to make the turn. So if you were a driver using this intersection, you might, as you're approaching the intersection wanting to turn left, you might not even go down into this lane. You'll probably check your rear vision mirror, and if there's no one behind you, you can make the left turn from the through lane. And if there's someone behind you, or if you know you need to slow down a lot, if you're a truck or something similar, then you'll indicate to get into this lane and then make your movement around. So again, there's lots of geometry. We have particulars on how far back this stop line needs to be positioned. We have definitions on the width at different areas, and this is basically to allow heavy vehicle movements of a consistent manner to get around the corner. And then we have some other geometries here as well, which tell us what the total length of the treatment needs to be. The longer version of this, the rural AULS, this is a longer treatment. It's more formalized. We have line marking, and this is, very much drivers are encouraged. I don't think it's legal to make the left turn from this through lane. I think you have to be in this lane, and all of the movements are designed. All of these radii are designed for the design vehicle. So if it's an articulated truck or if it's a B double or anything, then AutoCAD or similar programs will have turning movements with those heavy vehicles, and that's how this will be designed. And then basically anything that's wherever the turning treatment doesn't need to start, then we start the definition of this this treatment, how long it needs to be, what's the taper, and so on. Now we've got a couple of definitions here that I think are more or less the same. I don't see. So we've got the AUL-S and the AUL. Again, it's basically just changing in terms of the total length. That's really all. If we are in a rural setting, then we also need to provide a 1 meter shoulder at minimum, in addition to the lane width. So the lane width might be 3 or 3.5 meters for the left turn lane, plus we need a 1 meter shoulder at minimum. If you were to go and look up each figure that we were just talking about in the Austroads Guide to Road Design Part 4A, you will see that all of these dimensions are explained under the figure. We can read different lengths from tables, and we can determine different parts of the road geometry from the design vehicle, different parts of the curb return and that sort of thing. When I say curb return, that's this part. This part here is the curb return. So the curb return will come from the design vehicle, from an AutoCAD turning movement or something similar, and other parts come from design tables. So the first thing we do is we determine the warrants, so what kind of turning lane do we need. Then we work out what the lengths are, and then we can prepare an engineering layout. So we just do in 2 dimensions. This is the typical arrangement. It's been about 5 or in some places 10 years or so, where the practice has been we basically draw the 2D arrangement first, and then once everyone's happy with the 2D arrangement, then we go on to the 3D work. So that saves a bit of rework. So I'll give you a bit of an example. Again, I'm a developer. You're my designer. I ask you to go and prepare me a design for my turning lane. Now you could go straight to the 3-dimensional design based on one of these layouts, but if the road management authority disagrees with your length for D, or they disagree with your length for T, or if you make a mistake or something like that, then we come back here, and so you've done all this work on 3D, but you're going to have to redo all of that because you need to change the 2D layout again. So that's why it makes sense for us to prepare a 2-dimensional design. Then the 2-dimensional design will go to an authority to be checked and approved. And once the road authority agrees, then we go on with the 3D design, which is pretty common practice in a lot of planning arrangements. Again, let me just quickly check. What else do we have? All right. So I think we're going on to now part 4, 4D, stop/give-way signage. So give way and stop signs, these are what we refer to as uncontrolled intersections. If you check your key lecture questions for this topic, you'll see that question 10 is asking you what is an uncontrolled intersection. It's basically something other than a roundabout or traffic signals. So a roundabout physically controls movement, and traffic signals provide signaling control, but a give way and a stop sign, the signage is referred to as an uncontrolled intersection. There's basically nothing telling the driver exactly what to do other than their ability to read a sign and to use their own judgment as to how to cross the intersection. So give way signs and stop signs, these are the most common intersections in the state because they are the cheapest to construct, and we typically use them where volumes and or speeds are low. So all local roads give way or stop if they don't have good visibility, and it tends to be usually we'll have traffic signals and or roundabouts at the intersection of an arterial road. Sometimes there are just local roads, the intersection of 2 local roads. We might have roundabouts. There's quite a few in Ballarat. The intersection of 2 local roads might also be traffic signals, but more typically these tend to be traffic signals and roundabouts at arterial roads. Now the intersection control, the working part of this intersection, needs to be both the sign and the line marking. It's very important. As we'll see shortly, the line marking in some cases is critical. Give way signage, universally, this is everywhere in the world, give way signage is a red equilateral triangle pointing down. Whether it has the word give way in it or not, if you see this triangle, many places in Europe don't have any writing, they just have the shape, and you know that's a give way sign. Where we use give way signs is basically just dependent on good visibility. So as long as, if you're coming up to an approach and you can see a long distance to either direction or both directions, then give way signage is appropriate. That's really the only check for whether we should use a giveaway sign. Stop signage is universally a red octagon. Again, it doesn't really matter what part of the world you're in, it's always a red octagon, which is nice. It's quite a good thing that we actually have this universal, at least those two universal things. Not everything in traffic management is universal, but at least those parts are the same everywhere you go. Now, stop signs, these should be used where there is poor visibility. So here on Humphrey Street, if anyone knows this intersection, the intersection of Humphrey Street and Leith Street, you're approaching on Humphrey Street coming up a hill, and you really can't see what's coming until you're right where this white ute is. So particularly you can't see what's coming from the left. If you want to make a right turn, you basically have to be right on the stop line, and that's why this intersection is a stop, whereas the previous intersection around Lake Wendouree, this is quite comfortable being a give way because we've got plenty of visibility. If I check your key questions, so question 11 and question 12, where should give way signage be used and where should stop signage be used? That basically just depends on the visibility. If you've got good visibility, it should be give way. If you've got bad visibility, it should be stop signage. Simple as that. Now your next question, question 13, this is also visible on this slide. How wide are stop and give way line markings? So give way line marking is 300 millimeter wide with alternating 600 millimeter wide patches. So we have 300 millimeters wide this way, 600 and then a gap of 600, 600 and then a gap of 600 and so on. The only exception is at a roundabout, it's 400 wide instead of 300. The stop line marking is the same, so it's also 300 millimeters wide for a stop line, but it is solid. Now, another interesting fact, as I mentioned before, the line marking is critical because the regulatory, that is the legal part of the signage, is the line marking, not the sign itself. So if you come up to a sign that has a give way sign but stop line marking, or a stop sign but give way line marking, you are to legally obey the line marking instead. Now, an interesting part for anyone that knows, again, the city of Ballarat, this is Sturt Street. On the corner here, we've got the service station. On the other corner, there's a chemist, and I think we're just near, it's Pleasant Street and Sturt Street anyway. You might have noticed we've got traffic signals. So this intersection has traffic signals that control the movement, and there's a stop line marking here and give way line marking here. Same as here as well. So if you're stopped here on a red signal, and then you get the green light to go, you can go right across. If the light changes, or if you're coming around this way, you've got a green light and you turn left and you're waiting here, at this location, even if the red light is up in front of you, so it's red, you can go here legally. You can look, you find a gap, and you can go. That's give way. So you're legally able to drive through when the light is red from this position. Not from this position back here. Legally, you have to stop there when the light is red. But from this position, you're able to pick a gap and then enter that gap. So I'm excited to give you today's topic, or to this particular topic, because a safe system design is a particularly important development in the way that people think about road design and in the way that people really think about crashes and liability and what we are willing to trade off for the price of traveling. So it's and there's a lot of really interesting stuff in here that you probably wouldn't have seen before, and I think will change the way that you drive and change the way that you think about infrastructure investments. So in this topic, we're going to talk about safe system design. We're going to talk about safe system assessments. We'll talk about crash barriers. And we'll talk about signage and line marking. And as with our other weeks, if you go into the week 5 material on Moodle, you'll see that we have some key questions, and we also have some tutorial questions as well, which is just a bit of the tutorial questions are going to be just a bit of a thought exercise or a bit of a, I suppose, cooperative exercise, but we can do that in our next session. So topic 5, we'll get stuck right in. So this is safe system design. What does it actually mean? So in 2004, the Safe System Road Safety Vision was formally adopted nationally. It's Australia-wide, and it now guides the state's overall approach to road safety achievement. So Safe System has been developed for Australian circumstances, and it combines features from elsewhere in the world. So there's the Dutch Sustainable Safety and the Swedish Vision Zero visions or developments. So the Safe System comprises 4 cornerstones that work together to deliver greater benefits together than just each of their individual value. So the 4 cornerstones, I think, do I have them coming up in a slide? I think we do there. It's probably actually best to talk about this slide here. So the 4 cornerstones, and I think again this is one of your key questions. Question 1, what are the 4 cornerstones of the safe system? We have safe speeds, safe people, safe vehicles, and safe roads. In other words, we want to set our policy around speed limits such that they are keeping the sort of types of crashes which are possible in mind, and that we are not really permitting speeds which are going to be too unsafe around those dangerous intersections. We want to have safe people, so we want to have people that are informed about the best ways to drive, that are looking after their own safety as well as the safety of everyone else on the network. And this includes movements of pedestrians. So even if you're not in a vehicle, how do you enable people to move safely? We want safe vehicles, so we want cars and trucks that have adequate brakes, electronic controls. We want driver assistance technology. We want airbags and crumple zones. We want all of those things, and we want our roads to be safe as well. If you come off the Western Highway, we don't want you to hit a tree or a ditch or to just roll over in a paddock. We want you to hit a net that's been placed along the side of the road, the wire rope safety barrier, and basically just to come to a steady, slow stop with no unnatural or difficult forces on your body. So those are the 4 principles: speeds, safe roads, safe vehicles, safe people. So the safe system recognizes that there are limits to the forces that the human body can withstand. So if we're in a crash, basically if the forces are too large, if we have too much acceleration, deceleration, whatever you want to call it, that can be fatal. If not fatal, it can be permanently disabling or permanently damaging. So in the safe system, we seek to ensure that no road user is subject to forces in a collision which will result in death or any injury from which they cannot recover. That's the main idea. Now, part of this is recognizing that human error is a feature of the road transport system. Until we get rid of the humans, we're always going to have human error. We're going to get people doing this, trying to empty the last few crumbs out of a Doritos bag, presumably while driving at the same time. We can't eliminate that sort of mistake making, this tendency to take the eye off the road for a distraction. We can encourage people as much as possible not to do these things. For anyone who is guilty of Snapchatting while driving or sending a quick text or anything like that, please, I will just encourage you not to do that. Please just, if you've got to do it, if it's really important, pull over and do it. And if you can't have time to pull over and do it, it's not really that important. But nevertheless, we have to assume that people are going to keep making mistakes, and so we want a road system that's going to be forgiving of humans. So we recognize that people make mistakes, people are fallible, they often do make mistakes on the road, but we say that road trauma should not be accepted as inevitable. Despite the fact that we know that people will make mistakes, we shouldn't just say, oh, well, that's just the cost of doing business. That's why they've sort of stopped calling it a road toll. The concept of a road toll seems to imply that the toll is what you pay so that you can have a transport network. But the toll is measured in dead human beings, and we don't want to pay that toll. We don't want to think about it like that. I've sort of incorporated the Hard Luck Harold meme with this picture to try and encapsulate this is not okay. What's happening here? We should not view this as just being okay. And that's what the safe system model is trying to do. So instead, we try to say if a mistake is made on the road, the impact can be severely reduced or negated if we use the safe system model. That's the plan. So here are the four cornerstones which I discussed before, and you can see that they all feed in together. We've got safer speeds, safe vehicles, safe roads. We want all the physical forces on the human body to stay within tolerance. We want alert and compliant road users. This is compliant is road users doing the right thing, doing what they're told. So those are the four pillars. This one in the middle is what we want to see happen. We want to see physical forces on the human body stay within tolerance. And on the outside, this is what feeds into it. So we feed education and information into the road users to support them. We want to tell the road users, we want to test the road users on how they behave. We want to tell them how to act. We enforce road rules like speed limits and running red lights and stop signs so that we have more compliant road users. That's part of the enforcement arm. We have understanding of crashes and risks. This helps us to build safer roads. We can work on what's going to be problematic by looking at where crashes have occurred and seeing the number of head-on collisions with other vehicles, the number of side impact crashes with trees and with power poles. So those things all tell us what we can do to design a safer road. And then we also have admittance to the system. This is what type of vehicles are we letting into the system? We want safe vehicles into the system. So we don't want to import new vehicles to Australia. We're an island. Australia is an island, as I'm sure you're all aware. If you're not, good job of making it to university thus far. So Australia is an island, and we no longer produce cars here. So we have the ability to basically close our borders to the imports of anything except the highest 5-star safety rated cars. It'd be a great thing if we do that. I'm not sure what level of development a plan like that is at, but that's one way that we can significantly improve the the safety of our residents. This graph is really important, and I'm going to explain it quickly. So on the vertical axis, this is the risk of being killed in a crash. Well, it's not necessarily to say the risk of you being killed as the driver. This is the risk of someone dying. This is the risk of a death in a crash. And on the horizontal axis, this is the speed. So what we count as unacceptable in these graphs is about the 10% mark. So at 10% risk of someone dying, we have the 30-kilometer-an-hour crash with a pedestrian. So basically, if you have a pedestrian zone, lots of pedestrian zones in Victoria are, or rather areas with lots of pedestrians, they are signed at 40 kilometers an hour. But you can see if we increase the speed limit to 40 kilometers, we're up around 30% or more of those vehicle collisions, any collisions with pedestrians, becoming fatal. So not only do collisions become more likely with the higher speed, but they also become 3 times as deadly. Dropping the speed limit just 10 kilometers an hour to 30 k's in heavy pedestrian, built-up pedestrian areas gives us a significantly lower risk to the pedestrian safety. Let's go to the next curve. Side-on collision. Again, we have about 10% comes in at about 50 kilometers an hour. So 50 kilometers an hour, if you're involved in a side impact collision, there's a 10% chance that someone's going to die. How many intersections can you think of where there is a speed limit on either road, the main road or the side road or whatever, of 50 kilometers an hour or more, and it's a T intersection or a cross intersection where the impact angle is 90 degrees? I can think of, I couldn't name thousands, but I could literally be sure that there are thousands. And so again, we're saying like, well, we need to do things. We obviously are still going to have high-speed roads that intersect at right angles, but we need to do things to make sure that we minimize this chance of a side-on collision. How can we do that? What can we do to change the shape of the intersection so that at least the angle is not at 90 degrees, or at least the speeds involved in the angle are not going to have a vector sum of 50 kilometers an hour. And then finally, the head-on collision. And you might think of head-on collisions as being extremely damaging or extremely deadly, but actually cars have gotten very good at resisting fatalities in a head-on collision, and it's partly because we have so much space in the front end of a car. So the front end of the cars contain the crumple zones. There's lots of space in there to fit all of the bits and pieces that need to break down in the right way. So two cars colliding head on, if you're traveling at 70 kilometers an hour, and this is with zero braking, you're not slowing down before hitting at 70 kilometers an hour, there's still only a 10% chance that someone's going to die, because the cars are really quite good at that. So this diagram is one of the central sort of things that we think about in safe system design in terms of what is not tolerable, and what we need to do to minimize the risks of these curves. How can we shape the intersections, and other potential areas? How can we shape roadsides so that side-on collisions, head-on collisions, and pedestrian collisions are at the right speed and are minimized in risk? Another thing I want to point out, it's not shown on this curve, but a side impact, this is side-on collision between two vehicles. So one vehicle runs a red light and slams into the side of another vehicle. This is the curve for that. If you have your vehicle goes sideways into a pole or into a tree, you basically shift that curve 20 kilometers an hour lower. So it basically becomes the same as the pedestrian curve, because the side impact is very hard to design a vehicle there's basically no crumple zone. There's no way you can have the vehicle designed so that it's going to crumple around, and trying to sustain all of that weight around something unmovable like a pole or a tree. If you've got a car that's rated at 5 stars for side impact, the test that's done is basically to throw that car at a pole at 30 kilometers an hour. And if no one's hurt at 30 kilometers an hour, that's a 5-star rating. So if you're traveling any faster than that, side impact collisions, particularly with trees and poles, are exceedingly deadly, because there's basically nowhere you can help the car to not be hurt. So question 2 in your key lecture questions, A, B, and C, is what speed gives a 10% chance of causing a fatality for a pedestrian, a side impact, or a head-on? And I want you to answer that question as 30 Ks, 50 Ks, and 70 Ks. It's pretty easy to remember. 10% chance of fatality at 30 Ks for pedestrians, 50 Ks for side impact, and 70 Ks for head-on. So in thinking about roads and road sides, we know that the road network should be designed, built, and maintained so that the forces that road users are subject to in collisions should not give them a death or a serious injury. We also want to consider vulnerable road users by this. So by vulnerable road users, we mean cyclists, pedestrians, even motorcyclists. These are people which are offered no protection because they're basically not surrounded by a metal box filled with airbags and crumple zones. Anything that happens to them is basically just going to happen directly to their body. So if we have high-speed environments where crashes have a greater potential to be severe, you might also recall from your high school or first-year physics that the amount of energy involved in a moving object, it increases 4-fold when you double a speed. So if you go from 50 kilometers an hour to 100 kilometers an hour, you have 4 times as much energy to dissipate. Greater potential, much greater potential for a severe crash in high speed. So we recognize that crash severity can be largely prevented by the installation of flexible barrier systems. So these accommodate the driver error by absorbing the energy. This barrier is made of steel. I'll talk a bit more about the head-on treatment as well as the barrier itself, but steel is a very good material for absorbing mechanical energy in deformation, particularly if you have a hot-rolled section that has a great deal of ability to deform. So once it's struck, it's going to deform and change shape. It can change shape a tremendously large amount without breaking, without fracturing, and in changing shape, it's going to eat up energy. That's what it's designed to do. It's what these barriers are designed to do. We'll talk about this thing on the end in a minute. I'll show you a video about it because it's absolutely amazing. So that's what we want to do. We want to have these things that absorb energy, such as the steel barrier here or the wire rope barrier as well, which it's also steel but has a much greater flexibility. So in built-up areas where pedestrian and cyclist activity is high, or cross-traffic type crashes are more likely, we want to keep the speed low. We want to make sure that we've got, ideally 30k an hour in areas where pedestrian movements are most heavy. The center of Melbourne, you think about Melbourne as moving a lot of vehicles, and it does, but really the primary movement, the greater volume of movement in Melbourne is pedestrians, and yet we still have speed limits through Melbourne that are at 50, where sort of the risk to safety is, threatening pedestrians is quite high. In the centre of Adelaide, the speed limit is 30 kilometres an hour through the central drag. So the central main pedestrian area of Adelaide, we've got that speed limit that's shaped around the pedestrian focus, and again, I think that's quite a good thing. So speed limits alone are not enough. We also need traffic calming techniques. So we need road narrowing. We can use chicanes and surface texturing. So we can put some sort of roughness, horizontal roughness on the road. We can install some gateway treatments. So gateway treatment is basically something that tells you that your road environment has changed. If you are driving along say the Midland Highway, there are long sections of the Midland Highway where you're basically at 100 kilometers an hour and you're winding through rural countryside, and then you come to towns. And a mistake that drivers often make is not recognizing that they've come to towns, particularly at night. They don't recognize that they've entered a town, and so they maybe miss the first speed sign, and so they keep doing 100 or they keep doing 80, and the speed zone is down to 60. But a gateway treatment is something like a roundabout, or a significant line marking or flashing lights, or something that basically screams at the driver, you're entering a town, your traffic condition has changed. So all of these things can be used to calm traffic, keep the speeds low, and tell them that there's going to be pedestrians, there's going to be children, there's going to be cyclists, watch out. Let me just check we haven't missed nope. Okay, so the next key lecture question 3, is on this slide. What's the difference between primary and secondary safety in a vehicle? So primary safety is preventing a crash. And secondary safety is what to do after the crash has already occurred, or once the crash is in progress. So primary safety includes things like electronic stability control, automatic braking systems. We've got alcohol ignition interlocks. We've got lights that are on during the day to make you much more visible. If you're on a cyclist or if you're on a motorbike, you have some high visibility clothing, and again, lights that are on in all hours to help to prevent a crash before it even occurs. After the crash has occurred, seat belts and airbags, these are obviously amazing benefits to our safety, as are headrests and crumple zones and helmets for cyclists and motorcyclists. As I mentioned before, cyclists and motorcyclists still very vulnerable because a helmet is basically all they've got. They don't have any of the above. And they don't have anything electronic or automatic. They've basically got lights, high-vis, and helmets. That's their major safety stuff. Registration of roadworthiness also plays a part in ensuring that vehicles are kept up to a certain minimum level of safety, and we have new car assessment programs as well. So these are all ways of trying to improve the level of safety of the Australian fleet of vehicles, and to make sure that our road users are well protected. I'm not sure who MUARC is, but I took this set of slides from a road safety engineer that works in my office in Wendouree. So we provided the estimates that if we changed from all of our current cars to the safest car in the same class, we would have 1/3 fewer road fatalities. That's an estimate. So a pretty significant role that vehicle safety alone has to play. And this is without even talking about self-driving cars, which are absolutely going to be the next big thing in improving our safety. Now, for the safe system to work, it is necessary for users of the system to behave. So people have to follow rules, and they have to do the things that allow the system to protect them. We don't have any guarantees of protection. There's no guaranteed safety, but if people are taking risks in terms of driving in an impaired fashion with their mobile phone, or if they're driving drunk or driving tired, or if they're speeding. All of these things, unnecessarily changing lanes or cutting close or cutting people off, all of these things increase their risk. Another point to note, and the research is ongoing on this all the time, there's one school of thought that says that the more safety we provide to people in the road, the more people tend to compensate by feeling safe and taking more risks. So I'm not going to weigh in any further on that, other than to say that that's one discussion that comes up frequently. I think it'll be up to you to, as you develop your knowledge of the road space, to keep an eye on what varying official organizations are saying, or what the research is saying about road user risk taking, and to just keep an eye on the problem and be aware that that may be a factor as well in influencing the safety of our roads. Pardon me. So another part of this to look at is we want safer road users in our safe system. So we need the community to understand what the safe system is. We need the community to understand what we are hoping to achieve in the safe system. And trying to explain the benefit of different laws and different decisions that are made. So again, lowering speed limits is always unpopular. Nobody is happy with lowered speed limits. But if the messaging is right around the reasons why speeds are being lowered, it can at least help with people abiding by the speed limit, and therefore to get the protection that we were aiming for. So appropriate driver training, license testing is important. We've got a learner program in Victoria and elsewhere in the state. We have Transport Safety Services, TSS, which I think they've changed their name recently, but they basically look at they're like police specifically for heavy vehicles. We've got Transport Accident Commission advertising, so TAC advertising, trying to explain the risks of things like using a mobile phone while driving, trying to explain the risks of drink driving all the time, constantly. It's what's referred to as an adaptive challenge, getting road users to change their behavior, in that the challenge never goes away and you never solve it. You have to constantly work at keeping it at a minimum level of compliance, and trying to push that level of compliance up as much as you can, trying to constantly remind people, like, not to drink drive, not to be on their phones, and then to deal with new challenges, like trying to explain specifically to people not to do meth while driving, because meth heads won't listen at the best of times, but if you have at least a specific call out to people, that can be more helpful than a sort of a buckshot, don't drive impaired sort of type of message. Again, let me just quickly check the questions that we've got there. No. Okay, so a few safe system treatments that we can talk about. We have roundabouts, we have wire rope safety barrier, we have 40k speed zones, and safe system designs for signalized intersections as well. So we'll talk quickly about all of these. Roundabouts are one of the best things that we can do on the road network in terms of improving safety, and we'll explain why. It's explained reasonably well by these diagrams, but I'll sort of talk a bit about it here as well. So high severity crashes, when we say severity, we mean is it going to result in a fatality or a serious injury? High severity crashes are effectively eliminated at well-designed roundabouts. You basically can't have a high severity crash at a well-designed roundabout, because the roundabout physically forces you to reduce speeds on approaches. It makes you reduce speeds through the roundabout. It makes a reduction in the angle of impact. So if I've got two vehicles traveling along these dotted lines, where the two vehicles can collide, they're impacting they're almost traveling in the same direction. This is very different to a right angle impact, which has a much more likelihood of being dangerous or damaging. And we've also reduced the number of conflict points. So a conflict point in traffic design, this is the number of locations where one vehicle can hit another. In a typical intersection that's uncontrolled, we have 32 points where a traffic stream traveling in one direction can hit a traffic stream that's making a different movement. In a roundabout, we only have 8. So we have a significant improvement in the overall number of traffic points. I'll see if I can also look up, I'll quickly go to maps, and I'll try and find you a good example. I think some were recently installed up here on the Western Highway, Midland Highway. That one was already existing. Yeah, so this is a new roundabout that's been installed here. And what I want you to note is we're coming from the Midland Highway, so this is relatively straight, high speed limit road. Have a look at what happens as you approach the roundabout. The first thing is you see we've got traffic islands. We've got a very, and it's almost, you can't even see it here, but we've got a very gradual curve that comes in. The sort of center point of the curve is on this side. That's your first reverse curve taking you from 100 kilometers an hour. Actually, it might even be back out here. You can sort of see. The first curve taking you from 100 kilometers an hour down to 80. Then the second curve takes you from 80 to 60. Then the last one takes you from 60 to 40. And by doing this, you are forcing a driver to come down to 40 kilometers an hour before they have any chance of hitting another vehicle. The driver that's already in the roundabout is going to be doing 40 or 30 Ks as well. So you've got an impact in a well-designed roundabout that's going to be low angle and very much low speed. And it's almost impossible not to have that as the impact condition. So roundabouts are really safe for that reason. And that's why I've asked you to put some discussion into that for part of your question 4 for the key lecture questions. What makes roundabouts so safe? It's all of the reasons on this screen, and then some. Okay. Another safe system treatment is WRSB. This is wire rope safety barrier. So wire rope safety barrier, it's a braided steel wire. The importance of the braiding is that it helps the steel prevent breakages. The fact that it is wire in a sort of rope format means that it has a very long length over which it can deform. So if anyone remembers their material science, you'll recall that steel has an elastic range, but then it also has a zone of plastic deformation. Now these barriers, we actually put them under high tension, a lot of tension, so that they are, when they're hit, we don't want them to act like big rubber bands and fling people back into traffic. We want them to act more like a net. And the advantage of steel, as we discussed before, is that it eats up a lot of energy when it yields. So if it's already close to yield when it's under high tension, then you strike it, you're basically not getting any elastic rebound. You're getting energy absorption. You're getting these things that basically just chew up energy, and they stick cars to them. They slow them down gradually and pull them over, and they're very, very good at doing their job. So all of the steel post parts, you can see here, they're designed to break away. They have a little sleeve that gets put in the ground, so you can basically just come along, pull the old broken piece out, slip a new one in, reset the wires, retension it, and it's good to go. So this is a particular case example of a road, Lancefield-Tuberack Road. It's a high-speed environment. You can see all the trees here. If someone had to come off and hit those trees, it certainly wouldn't be as forgiving as hitting this wire rope safety barrier. So there was roadside vehicle debris, and obviously the barrier has been hit because it's been damaged itself. No sign of the vehicle and no reported injuries. So basically someone hit this thing and then they just pulled off and drove away. They didn't need to call anyone. They didn't need to do anything like that. Now, ideally, what the state would like you to do, if you hit a barrier like this, you've got third-party insurance on your car, you should call it in and cover it on your insurance, because this thing costs a lot to repair, and it's honestly like the insurance company should cop that as well. But what tends to happen is the state just eats up a lot of the cost, because people, they perform so well at stopping vehicles from having a bad crash that the vehicles just drive away, and they don't think anything more of it. So that's a good thing for the vehicle operators, and it's a good thing for the state as well, in that the cost of a human life is very high. We don't want to see people hurt or injured. We also don't want to see the economic impacts of that as well. But the economic cost of repairing this thing is still is still there as well. So yeah, we would say compared to no barrier, especially compared to where there are trees or poles or a drop-off or some other sort of hazard, these barriers have a crash reduction factor of 90%. You might think that if there was just a field, like let's say this road was pretty flat and you basically just had an open grassy field, why do we need a barrier? What do we need to stop the vehicle from going out into the field? Wouldn't you just run off forever? But what tends to happen is that the field is so much more rough than the road, or in winter it's so much softer than the road that in reality you don't just run off forever. The vehicle will flip or roll. And in a rolling scenario, the vehicle occupant is much more likely to be injured than if they were to hit this barrier. Do we have questions about barriers? No. Okay, here's another example of a different scenario. So we have Dalesford Trentham Road. This is another high-speed environment. There is lots of roadside vegetation. In this case, there were no wire rope safety barriers. When a vehicle left the road, it hit the steep embankment on the side of the road, and all occupants had serious injuries. So this is an excerpt from the police report. The vehicle was travelling west along Dalesford Trentham Road, approximately 400 metres west of Islay Lane. The vehicle travelled around a slight left-hand bend. They lost control in the wet and travelled to the opposite side of the road before colliding with a small embankment, which then caused the vehicle to become airborne into a large tree. So the impact of the tree was above ground level. All three occupants serious injuries. 2 ambulances and to the Royal Children's, and the driver by road ambulance to Royal Melbourne Hospital was needed. So very severe crash. That's the sort of difference between providing the barrier and not providing the barrier. Now, I think I've discussed in the past that as a state, we can't afford to put these barriers literally everywhere. We have thousands of kilometres of road, and the barriers cost about $1 million per kilometre to put in, plus there's an ongoing maintenance cost. So we literally it's just an impossibility to put it on every road. But if we put it on the higher risk or higher traffic roads, and over time, if our vehicles become smarter, if our vehicles are self-driving, they will be the key marker in getting us towards zero road fatalities. If we need more capacity at an intersection, then a roundabout is not going to be good enough. We're going to need to go to traffic signals. But traffic signals depend upon the road user doing the right thing. Traffic signals work when everyone is obedient, and when people are disobedient, there's a big problem, because there's really nothing physically that stops you running straight through a set of red lights. There's the threat of a fine and the knowledge that running through that set of red lights is probably going to injure yourself or someone else, but there's nothing that physically stops you, especially if you're tired or distracted or otherwise unable to do the right thing. So one of the ways that we can help to give further physical changes in the road that will help prevent speeding and help prevent abuse by users of the road is this idea of a raised platform intersection. So it's still a signalized intersection, but we have this part here where this ute is currently sitting on. This is a raised platform. So I think this whole intersection is raised, but basically on approach, you have a vertical lift. So there's a subtle vertical deviation on the approach to the intersection, and it gives vehicles more encouragement to slow down than if they just had a straight flat road. So it tells people more clearly, especially if they're drowsy or distracted, that, hey, you're about to hit something. Even if they just feel the road jump up and their eyes are somewhere else, their probably first instinct would be to brake. So that can be really helpful at trying to get that speed down to about 50 k's an hour. You can see here the yellow sign is for an advisory speed limit of 40. 50 k's, we're reducing that impact of a side impact crash, of the severity of a side impact crash, to give us much less likelihood of a fatality. If people do adhere to 40 as they go through the intersection, even better. Even better. Then we're down to an almost zero chance of a fatality in a side impact crash. Okay, so that's the safe system. Briefly, we've talked about what it actually is, and it's about the 4 pillars. It's about trying to be forgiving to drivers. But what are safe system assessments? Let's have a bit of a chat about that now. So I'll give you a hypothetical scenario. Let's say that you are planning a new highway bypass of an existing town, and the new highway route will intersect with several existing roads. Pardon me, a little bit yawny this point in the afternoon. So what kind of intersections should be used and why? We've got this is a proposed road. We've got all these existing roads. How do we want these roads to intersect? What kind of, do we want traffic signals? Do we want roundabouts? Do we want, what sort of cross section do we want the highway to take? Do we want 2 lanes, 4 lanes? Well, that's a volume question. Maybe we know what the volume is. But what about the shoulder? How wide should the shoulder be? And do we need barriers or do we need something else? So all of these questions are safe system questions, and that's how we can justify these decisions is we perform a safe system assessment. So a safe system assessment, this is the best way to determine what treatments need to be used for road improvement works at the planning stage. So that's an important part as well, is that we're coming in at planning. There are other safety tests, like road safety audits, that we will do after we have planned out works. But safety system assessments are best when we are planning. We don't even know what we're going to build yet. We haven't even got we haven't got a 2D layout plan. We've got a concept plan at best. Then we go on to doing a safe system assessment. So the safe system assessment looks at exposure, it looks at likelihood, and it looks at severity. So exposure, these are sources of crash risk. Likelihood is the chance of a crash risk, and severity of different crash types. This is what's the consequence. Is it a fatal accident? Is it a a fender bender? That sort of thing. Again, just let me quickly check. Question 5 in your key questions: at what stage of project development should safe system assessments be used? This is at the planning stage. And your question 6 is going to ask you to define exposure, likelihood, and severity, which will be coming up soon. So Austroads has published a safe system assessment framework that details how an assessment can be made. So one key component of the safe system assessment is the matrix that you see below. So this matrix, it looks at exposure, likelihood, and severity, and it looks at 3, 4, 5, 6, 7 different types of crashes. This is the basic safe system matrix. We multiply these together, so 4 by 4 by 4 is 64. 64 times 7 is 448. The biggest score in a safe system assessment is 448, but it's like golf. You want to get the lowest score possible. Lower score, the safer the design. Now, a safe system assessment is not an absolute tool. It's a relative tool. It's useful to compare a single design option. So if we're looking at options for a single design aspect, and this is because it's subjective. A safe system assessment cannot tell you that the intersection of Sturt Street and Latrobe Street, or the intersection of well, that's a bad example because those roads don't intersect. The example of Wiltshire Lane and Glenelg Highway, or Wiltshire Lane and Latrobe Street, it can't tell you if either of those intersections is safer or if either design is better. But what it can do is, if you were looking at, again, our hypothetical situation a couple of slides ago, if you were looking at a raised platform intersection or a roundabout or a grade separated intersection or anything like that, it can tell you what is better there. So that's what we want them to do. They're a subjective tool. They use a qualitative assessment, but they help to compare different treatments. So 2 safe system assessors, that is to say 2 different people, will find a different total score when looking at the same intersection. That's how it works, because the assessors are subjective themselves. They're going to make their own assessments. One person might think that the exposure for an intersection type crash is a 3. Another person might think the exposure is a 4. It doesn't really matter what individually they score this as long as they will, if 2 assessors were to check options for the same design, they might get different scores, but they should both find that the same treatment has a lower score. So they won't find exactly the same numbers, but they will find that they're tending to point the design direction the same way. They're both tending to point towards a raised platform intersection, or they're both tending to point towards a roundabout. Okay, so here's questions 6, A, B, and C are coming up. What is exposure? Exposure in safe system assessment is the chance that a crash type could occur. If you have no pedestrians, you cannot have pedestrian type crashes, so the exposure is 0. If you have no motorcyclists, you cannot have motorcyclist type crashes. If you have a small number of cars, you have a small exposure for car type crashes. If you have a very large number of cars, you have a large exposure for car type crashes. That's basically how exposure works. Likelihood, this is the probability that a particular crash type will occur. It's a roll of the dice. It's saying, is it high or medium or low chance that a particular crash type could occur? So a head-on collision could occur with a wide painted median. So here we've got a wide painted median. But the head-on crash is less likely than if there was no separation. So if we just had 2 lanes and one single thin line between, a head-on crash would be more likely, so we would have a greater likelihood. And then in the case of the wide median, we decrease the likelihood there. Now severity, this refers to the consequence of a crash. So severity, this asks us if we're just going to scratch some paint, or it asks us if the one second, sorry, my partner just gave me some distressing news. I'll need to deal with that in a minute. So the severity tells us, are we going to scratch paint, or are we going to have an injury or a fatality? Any of these things may be rated on the severity scale. So speed is one of the most significant things that factors into this, but as does the risk for the individual road user. So if it's people in well-protected cars, or if it's in people relatively unprotected as cyclists or pedestrians. So we'll keep talking about safe system or safety-related things in chatting a bit about crash barriers, and I'll just give you some of the basic overviews. There's lots of different types, which we'll go into in small detail. All right, so you'll probably have noticed that we no longer build staircases without handrails. For many years, roads were built without safety barriers, and now we've started to see some different thinking. We used to target black spots. We used to say, oh, someone fell off on this step, so we built a bit of handrail just there. Or someone fell off on the 8th step, so we built a piece just there. These black spots were sort of thought of as the areas we needed to proactively, or not proactively, reactively fix the roads. But now we recognize that crashes can occur anywhere. So by using a continuous safety barrier system, we're able to target potential future crashes. We're able to sort of do a lot better at that kind of thing. So if you want to see details of acceptable barrier products in Victoria, you can see that there are a series of road design notes that are prepared by Vic Roads, and this one in particular, 0604, specifically talks about acceptable barrier products. These are the approved barrier products list. So this list is constantly being updated every few months as new materials are tested, as new barrier types are approved for different loadings of vehicles and different speed environments. This detail is updated. And if you check your key lecture questions 7, where can information on acceptable safety barriers in Victoria be found? This is in Road Design Note 0604. So there's heaps of road design notes produced by Vic Roads on all sorts of things. 0604 is what you want for safety barrier. Barriers come in many types. So we've got, it's visible in this picture, we've got barriers that protect pedestrians on this overpass. We've got longitudinal barriers that protect from a drop-off. We've got an end treatment barrier. We've got, barrier fence. And in the distance there, we've got some sort of a heavier concrete or steel barrier. So all sorts of barriers are used, and they just sort of change depending upon what particularly we need them for. So we have one kind, and again, if you check Road Design Note 0604, these are some of the definitions in there. Permanent flexible barriers. These barriers are a permanent part of the road, so they're not temporary for roadworks. They're ongoing protection of a hazard or ongoing protection of vehicles. And they're flexible, meaning that they absorb energy in a crash. So these ones, these are the wire rope safety barrier. This is our sort of standout, permanent, flexible energy barrier. Now, the biggest downside with these ones is that they need maintenance when they're struck. Basically, if they have protected one car from a crash, they are not effective in that same location until they are repaired. Another point I want to raise about these safety barriers is they are not designed for every vehicle. If you have a truck will have some chance of being contained, but a big B double or something like that, especially hitting at a high angle, it's just not going to be held in place by these barriers. They're way too big. A motorcyclist will tend to either hit the barrier and fall off over the top, because the motorcycle and the motorcycle operator are two separable units. The driver of the bike tends to hit the barrier and fall over the top, or if they've fallen off before they hit the barrier, they slide into the poles and hit them at the base. So in either case, these are not particularly great for cyclists, for motorcyclists, but they are not the cheese grater that gets talked about. There's never been a single case of anyone being cut by these things. They tend to just slide into the bases and be injured, the same way they would be sliding into the base and hitting a pole, or sliding into the base and hitting a tree. If you have a very low car, like a Ferrari or a Lamborghini or something, that would go straight under the barrier. Because again, the barriers are designed with a certain amount of tension. They're designed for the 85th percentile vehicle height. It might be 95th percentile, I can't quite remember, of vehicle heights, but it certainly doesn't cater for everything. However, if you can contain 95% of the vehicles that are on the road and help keep them on the road, that's a really good outcome. We have permanent rigid barriers as well. So rigid means that they do not deflect when they're hit. These are concrete barriers, as you can see. They're fixed into the road pavement. They're fixed into each other. These things they'll contain a tank just about. And they are they offer no energy absorption, so you basically just bounce off them if you hit them. If you hit them full on, you don't have any sort of energy absorption to help bring you to slow down there. But they are very useful in areas where we cannot afford to frequently repair crashes. So in this part of Melbourne, this is just near the Westgate Freeway, or just on the Westgate Freeway, the volumes of traffic are so high that if we were to have to come out here, once a week or twice a week and repair a damage to a barrier, it would actually be more unsafe to the road workers fixing those barriers than it would be to permit the vehicles to strike the barrier. So the barrier here, it prevents head-on crashes, or it prevents sideswipe crashes, and it's a traffic control device. But we could not afford a flexible barrier here because the maintenance would just be too unreasonable. In between the rigid and the flexible, we have semi-rigid. So here we've got a combination of a barrier curb and a steel W-beam barrier. So this W-beam barrier, it's more flexible than concrete. It's less flexible than the wire rope safety barrier. It does a good job of containing vehicles while absorbing some energy. And depending on the collision, if this barrier is struck, it could be struck again or even a third time and still offer some protection to vehicles before it needs maintenance. Or rather, maintenance will be scheduled as soon as it is struck, but the maintenance might not be able to occur straight away. So it's able to do a better job of providing that protection. So some energy attenuation compared to rigid barriers, less maintenance than flexible barriers. Now we've got enter into a class of barriers as well, which are temporary. So we've got temporary plastic barriers that are water filled. These temporary barriers are very useful during road work or for other temporary traffic management. So if you see on Gilly Street at the moment, the intersection of Gilly Street and Gregory Street, there are a number of temporary water-filled barriers that have been used there. And these barriers are basically to control movements into Gregory Street in a safe manner while the Regional Roads Victoria upgrade is being built. So the City of Ballarat wanted Gregory Street open, and the temporary barriers were a way to do that. Now, to be effective, these barriers must be filled with water. They're called water-filled, not, I guess, hydrophilic. They're not, they don't like water, they need water. They also need to have a minimum length, and they need to have appropriate end treatments. So you need a certain number of these joined together. They need to be filled with water. Quite often, I've been to inspect traffic management, and these are simply not filled with water. Or maybe every second barrier is filled 1/3 to half the way full, and every barrier needs to be fully filled for them to be effective. So putting them up on a road where you've got workers behind them and expecting those workers to be protected without properly filling them, it's really quite hazardous. In fact, this can be more hazardous because where the vehicle comes off and strikes the empty barriers, the whole chain of barriers, they're all linked together, will go flying. Now, even when they're filled with water, these barriers move over a meter when they're struck. So if you find yourself on a job site and you're working around these barriers, don't think of the barrier as a solid wall, because it absolutely is not. Don't lean up against it. Don't stand too close to it. Give yourself at least a meter's clearance between yourself and that flexible barrier or temporary barrier, because if a car or a truck hits it, it will go flying towards you and it will cause just as much injury as the vehicle itself. Now, I want to talk about end treatments. So I promised before that we would come back and talk about one of these really cool end treatments on a W-beam barrier. And here you can see the importance of appropriate end treatments on vehicles, on barriers, because this vehicle has been speared by a barrier. So the barrier that's there ostensibly for safety purposes, if it's not designed correctly or if it's not put on properly, you can see that the end of this barrier, it's still a stiff steel section. It has pierced the radiator. It's dodged, I guess, anything solid enough in the engine. It's come up over the inside canopy and gone straight out the back. Now, in this particular case, nothing grisly happened. No person was speared, but that can happen. And it's therefore appropriate that we don't just have these barriers that terminate in a little, I think they're called like a fishtail end. If you go driving around and looking for barriers, you'll see old barriers where they just basically have a short length and a little, sort of looks a little bit like this. You've got the barrier, and then the end is just like it's almost a little fishtail. There's really nothing to it, nothing to stop that spearing through the vehicle. So we need to make sure that where the barriers start and stop, the barrier itself is not made to be a hazard. I've got some questions that we skipped over as well. So question 8 and 9 in your key questions. What are the pros and cons of flexible and rigid barriers? Those answers were on the last couple of slides. And question 9, why should people exercise great caution around plastic water-filled barriers? That's because, as I mentioned, they can move a lot. Okay, so end treatments. There are a number of end treatments available that prevent vehicle spearing and encourage the steel barrier section to deform in a controlled manner. These absorb a lot of energy and they bring vehicles to rest slowly. Collectively, these treatments are known as gated redirective energy absorbing terminals, or GRATE. They're very effective, and we'll watch a short video now. You really want to see the benefit of those things in absorbing energy when the vehicles strike the end treatment, and that steel is made to deform in that way. It's taking energy away from anywhere that it can do any harm. It's not storing it in a spring or raising it up in height, in gravitational potential energy. That energy is being used up in deforming the steel. So yeah, they're very, very safe things. Sorry about that, guys, for the mute. Thanks for letting me know. Okay. All right, so there's some other barriers in here that are worth noting as well. So we've got quite a few visible. In the center here, we've got a W beam, and then underneath there's more steel. We call this rub rail. So this is put in place for motorcyclists. And again, the idea is if the motorcyclist comes off, we don't want them to hit the steel posts. The rub rail lets them slide along. And sliding, if they're wearing leathers, is quite a safe way for them to lose speed and not be injured. We've got crash energy absorbing bollards, which are again quite useful. They've got a kind of a special base that's concreted in place, and then when they're struck, they're able to eat up some energy in deforming a small distance. This treatment here is called a raptor or something similar, and it basically it clips around a pole where you don't have much space to protect the pole, and if you strike it, it tends to twist, and so it pushes a vehicle away from the pole rather than striking straight into it. There are some steel barriers instead of concrete ones. There are barriers that just attach to a truck, so you can drive along your mobile traffic protection area. You can just work in this space here, and you've got quite good mobile protection. So yeah, lots of these other types of things. If you're interested in more details, go and see Road Design Note 0604. All right, the last thing we're going to talk about today is signage and line marking. So signage and line marking are very important. They're very useful in road design. We want to make sure that we get them right, but we should not just depend upon signs, and we should not just depend upon line marking in place of other treatments. Signs can be ignored and hit. Line marking as well. You can see here this is someone overtaking when they really shouldn't be. People can ignore these things. Physical protections like proper shaping, concrete shaping of intersection designs. This is a much better way to avoid and protect against crashes rather than just signage and line marking. Oh, pardon me. Drivers have a limited amount of attention as well, so we can't really. This is a classic example of just way too many signs in a short space. We cannot split driver attention too many ways. So this includes not only providing too many signs, but it includes it gives us information on how large signs need to be. So you probably haven't noticed before, but the next time you go driving, take a look out for it. Have a look at the size of a 100-kilometer-an-hour speed limit on the freeway compared to a 60-kilometer-an-hour sign on a local road. The 60 sign will be, maybe a foot and a half wide. The 100 sign will be more like 4 foot wide. They're absolutely massive. You tend not to notice them because you're used to reading them at a certain distance. And the same thing is true of the green directional signs that are around the state. They have minimum lettering heights so that they are visible from 100 meters away or 150 meters away, depending upon the speed limit. So on the freeway, the letters are, 300, 400 millimeters high in some cases. They're really quite big. And in local roads, they're much smaller because you can read them at a much more comfortable speed and a more comfortable distance. Another note on driver attention is variable message boards. So you might see the boards that are electronic messages, and they change or they cycle through to give you some kind of warning about upcoming roadworks, something like that. Those signs should only have two different signs on them. So they shouldn't cycle through 3 or more because the driver just can't read them, and they should only really have 3 or 4 words on each slide. Otherwise, again, the driver just can't read them. So a lot of the times people try to fit in too much information on those variable message boards, and it's just lost. The driver just physically can't take that in. So in Victoria, there are many different types of sign used. We have regulatory signs, which are red with black, like you see here. So these are regulatory, meaning they are legal. You have to obey them or you can be fined. We have advisory signs in yellow. So these have no legal weight. You can ignore these at your peril. If you are not a truck, you can go more than 35. Even if you are a truck, legally you can go more than 35. You can go up to whatever speed is posted here, but you might roll over if you are a truck. The direction signs are in green, as we were talking about before. These are, again, really like if you think about it, that's quite large lettering. This gantry, the bottom of that gantry is at least 5 meters high to let B doubles pass under it, and then you can see the size of the sign on top of that. So it's absolutely huge. By the way, you see this, this is how a lot of these end treatments used to be done. This type of treatment is not used anymore. The rounding on the end is designed to stop the barrier spearing through a vehicle, but it's not as effective as we would like. The gated redirective energy absorbing terminals, those are much better, and they are the only ones that get installed fresh today. We have tourism signs which are in brown and information signs in blue as well. And we've got a special class of sign as well, which are CityLink signs in blue with yellow. They're quite unique. And of course, these are all just the information signs. We have hundreds of other kinds, which I'll chat about briefly in a sec. I'll talk quickly about how to display signs on plans. So the most common types of signs talk about keep left, no right turn, one way. We have so many of these. I'm not going to discuss all of them because literally we'd be here all day. We could have hundreds of slides just on all the different kinds of signs that get put in. And I'm no expert on signage. If I need to find out what kind of sign is best to install to communicate something to a road user, I check with people in our road safety team. And similarly, if you're looking for the right kind of signage to use, you can seek advice on that to find out what's going to be best. But I do want to talk to you about the way that we draw signs on an engineering plan. So a sign is simply represented like this on an engineering plan. The circle is representative of the post that holds the sign up, and then the straight part is the sign itself. So the direction that the sign faces is away from the circle. So the sign faces this way. This is the way the sign faces, and we read the sign this way. So hopefully that's pretty clear. Right, a couple of questions, 11 and 12. Why should signage and line marking not be dependent on in design? As we discussed before, signage and line marking are the easiest things to ignore. And question 12, how are yellow speed limit signs different from red, white, and black signs? It depends on what is advisory and what is legal. So that's it for this lecture. Now, on